Welcome. Friends, I'm so glad you're here. Whether you're drifting towards sleep, unwinding after a long day, or simply looking for a quiet companion, you found the right place. Before we begin, I'd love to know where in the world are you listening from. Perhaps you're wrapped in a blanket, sitting by a softly lit window, or resting somewhere under an open sky. Wherever you are, I hope you're warm, comfortable, and ready to wander with me into Earth's most extraordinary architectural project, the 4.5 billion year construction of a living world. If you find peace or curiosity in these gentle stories, please consider liking the video, subscribing to the channel, or sharing it with someone who might need a moment of stillness too. And to those who've already joined along, thank you. 4.6 billion years ago, in a region of space that will one day be called the Orion Arm, a molecular cloud begins its slow collapse. The cloud spans dozens of light years, yet its destiny unfolds with the precision of a master architect's blueprint. Here, in the cold emptiness between stars, hydrogen atoms drift in concentration so sparse that each cubic centimeter contains fewer particles than the best vacuum chambers human technology will ever achieve. Yet even in this near-perfect void, gravity begins its patient work. The collapse takes millions of years, imperceptibly slow by any measure except geological time. As the cloud contracts, it rotates faster, spinning like a figure skater pulling in her arms. The conservation of angular momentum, a law as fundamental as existence itself, transforms a roughly spherical mass into a flattening disk. At the center, where material falls fastest, temperatures begin to climb. Hydrogen atoms collide with increasing violence until nuclear fusion ignites, birthing a star that will burn steadily for 10 billion years. Around this new sun, gravity sorts particles by mass with the methodical precision of a cosmic construction crew. Heavy elements iron, nickel, silicon settle into inner orbits where stellar radiation strips away lighter compounds. Hydrogen and helium, too energetic to condense in the heat, drift outward to cooler regions where they will eventually form gas giants. Between these zones, at precisely the distance where water can exist as solid, liquid, and vapor, conditions align for something unprecedented in this corner of the galaxy. The temperature gradient follows curves that seem almost intentionally calibrated. Too close to the sun, and volatile compounds vaporize into space. Too distant, and everything freezes into permanent ice. But here, 93 million miles from the nuclear furnace, the equilibrium temperature hovers near the triple point of water. Scientists call this the habitable zone, though the term hardly captures the exquisite precision required, a mere 5% closer to the sun. And Earth would have suffered the runaway greenhouse effect that turned Venus into a hellscape. 5% farther out, and the planet would have frozen into a lifeless snowball. Within this Goldilocks region, dust grains begin their ancient dance of accretion, each particle no larger than a mote in sunlight, yet guided by electromagnetic forces that cause them to stick when they collide. The process unfolds with industrial efficiency. Microscopic specks clump into larger aggregates, which attract more material through their growing gravitational fields. No conscious mind guides this assembly, yet every collision follows the same physical laws that will later govern the orbits of spacecraft and the trajectories of thrown baseballs. The disk rotates with mechanical regularity, completing one revolution every few thousand years. In this cosmic clockwork, objects in similar orbits move at nearly identical speeds, allowing gentle encounters that build rather than destroy. Dust grows into pebbles, pebbles into boulders, boulders into planetesimals dozens of miles across. Each step in the process occurs at exactly the right pace, fast enough to avoid being disrupted by stellar winds, slow enough to prevent catastrophic collisions that would shatter the growing bodies back into fragments. Scientists studying meteorites from this era find evidence of temperatures reaching 1500 degrees Celsius, hot enough to melt rock and separate heavy elements from light ones. This thermal processing sorts materials with the precision of a cosmic foundry. Iron and nickel, dense and refractory, sink toward the center of forming planetesimals. Silicate minerals, lighter but still substantial, form mantles around metallic cores. The most volatile compounds, water, carbon dioxide, organic molecules either vaporize entirely or migrate to the coldest outer reaches of the system. Within 10 million years, a geological instant that nonetheless spans more human lifetimes than have ever existed, Earth reaches nearly its current size. The protoplanet sweeps its orbital path clean with gravitational efficiency, gathering material like a cosmic vacuum cleaner. Each impact adds not just mass, but angular momentum, setting the planet spinning at precisely the rate needed for stable weather patterns and manageable day-night cycles. Too slow, and temperature extremes would make the surface uninhabitable. Too fast, and atmospheric dynamics would become chaotic storms. The surface during this period glows cherry red from the heat of constant bombardment. Impacts arrive with the regularity of heavy machinery, each collision releasing more energy than all of humanity's nuclear weapons combined. Yet even this violence serves the greater architectural plan. Large impacts vaporize rock and create temporary atmospheres of silicate vapor. Smaller ones deliver water trapped in asteroid ice and organic compounds synthesized in the cold depths of space. The bombardment appears chaotic, yet follows predictable patterns based on orbital mechanics and gravitational resonances that mathematicians will not discover for billions of years. Between impacts, the planet begins its first attempts at differentiation. Radioactive decay of aluminum-26 and iron-60 heats the interior, while the constant rain of debris keeps the surface molten. Under these conditions, dense materials sink toward the center, while lighter compounds rise to form a primitive crust. The process occurs with the methodical precision of a sorting algorithm, governed by density differences measured to the third decimal place. Iron and nickel form droplets that merge and descend through molten silicate, eventually coalescing into a metallic core that will generate Earth's protective magnetic field for eons to come. In the outer regions of the growing planet, where temperatures stay below the melting point of rock, a different process unfolds. Here, volatile compounds can survive in solid form, locked away in mineral structures, or frozen as pure ice. These reservoirs will later provide the water for Earth's oceans and the carbon for its first organic molecules. The distribution follows thermodynamic principles so precise that chemists will spend centuries mapping the relationships between temperature, pressure, and chemical stability that govern these ancient processes. The mystery that haunts planetary scientists is how this apparent chaos produced such an ordered result. Random collisions and gravitational interactions somehow generated a planet with exactly the right mass, composition, and orbital characteristics to support life. The odds against such a confluence seem astronomical. Yet here exists the evidence, a world whose every parameter appears fine-tuned for biological complexity. Whether this represents cosmic design, anthropic selection, or simply the universe's capacity for self-organization remains one of science's most profound questions. As the bombardment gradually subsides, Earth settles into its current orbit with the precision of a master clockmaker's final adjustment. The planet spins once every 24 hours, orbits the Sun once every 365 days, and tilts at exactly the angle needed to create seasons without extremes. Only took 10 million years to build a world. Yet the project timeline stretches ahead for billions more time enough for oceans to form, life to evolve, and consciousness to emerge and contemplate its own unlikely existence. The bombardment slows, but Earth's most crucial construction phase begins in earnest. Within the planet's molten interior, iron droplets no larger than raindrops start their long descent toward the center. Each droplet follows the same inexorable path, pulled downward by gravity through a maze of liquid silicate rock. The journey takes thousands of years for individual droplets, yet the collective migration unfolds with the efficiency of a massive industrial process. Scientists call this the iron catastrophe, though catastrophe suggests sudden disaster rather than methodical planetary engineering. The iron sinks because density governs everything in a molten world. At the pressures and temperatures deep within the early Earth, iron weighs nearly 3 times as much as the silicate minerals that surround it. This difference, measured in grams per cubic centimeter, drives one of the most important sorting operations in planetary history. Dense metallic particles merge as they descend, forming ever larger masses that carve channels through the molten mantle. The process accelerates as gravitational potential energy converts to heat, raising interior temperatures high enough to keep the iron liquid during its entire journey to the core. Within 50 million years, still rapid by geological standards, Earth completes its differentiation into distinct layers. The metallic core occupies the innermost third of the planet's radius, containing nearly all of the iron and nickel that accreted during formation. Above this lies the mantle, composed primarily of silicon, magnesium, and oxygen arranged in crystal structures that remain stable under crushing pressure. At the surface, the lightest materials form a thin crust that floats like scum on the molten interior. Each layer maintains its position according to density gradients so precise that seismologists billions of years later will map them using earthquake waves. The newly formed core begins generating Earth's magnetic field within a few million years of its completion. Liquid iron moves in convective currents driven by heat escaping from the planet's interior, creating electrical currents that spiral through the metallic fluid. The geometry follows the same principles that govern laboratory dynamos. Rotating conductors in magnetic fields generate electric currents, which in turn produce magnetic fields. The feedback loop creates a self-sustaining system that has operated continuously for over 4 billion years, requiring no maintenance or external power source. This magnetic dynamo produces effects that extend far beyond Earth's surface. The field deflects charged particles streaming from the young sun, creating the first version of the magnetosphere that still protects the planet today. Without this invisible shield, solar wind would strip away any atmosphere that manages to accumulate, leaving Earth as barren as Mars. The field lines stretch into space for tens of thousands of miles, forming a teardrop-shaped cavity in the solar wind that encompasses the entire Earth-Moon system. Scientists studying other planets find that magnetic fields correlate strongly with atmospheric retention worlds. Without dynamos lose their air to space, while those with strong fields maintain thick atmospheres for billions of years. The core's structure becomes increasingly sophisticated as cooling progresses. The innermost region, where pressures exceed 3 million times atmospheric pressure, solidifies into a sphere of nearly pure iron and nickel. This solid inner core grows slowly outward as heat continues to escape, but the process maintains a precise balance. Too much cooling would shut down convection and kill the magnetic field. Too little would prevent the formation of the solid inner core that helps drive the dynamo. Earth's core finds the optimal cooling rate automatically, governed by heat transport equations that maintain the delicate balance between solid and liquid phases. Geophysicists measuring seismic waves discover that the solid inner core rotates slightly faster than the rest of the planet, about 1 degree per year faster than the surface. This superrotation results from electromagnetic coupling between the inner core and the liquid outer core, creating a planetary gear system of extraordinary precision. The differential rotation helps maintain the complex flow patterns that sustain the magnetic field, while magnetic torques prevent the inner core from spinning too fast or too slow. The system operates like a finely tuned mechanical clock, except the components are thousands of miles in diameter and composed of molten metal at temperatures exceeding the surface of the Sun. Deep within the core, pressures become so intense that iron atoms pack into crystal structures impossible at Earth's surface. The hexagonal, close-packed arrangement allows maximum density while maintaining the electrical conductivity essential for magnetic field generation. These crystals align preferentially along Earth's rotation axis, creating seismic anisotropy that geologists detect by analyzing earthquake waves that travel through the inner core. The alignment suggests that the solid inner core remembers the direction of the magnetic field when it crystallized, preserving a record of Earth's ancient magnetism in its very atomic structure. The heat driving core convection comes from multiple sources, each contributing to the precise energy balance required for magnetic field generation. Radioactive decay of potassium, uranium, and thorium provides steady background heating that will continue for billions of years. Gravitational potential energy releases as the inner core grows and denser materials continue separating from lighter ones. Primordial heat left over from Earth's formation slowly leaks outward through the mantle. The total heat flow measures about 44 terawatts, enough energy to power human civilization many times over, yet barely sufficient to maintain the convection currents that generate the magnetic field. Studies of ancient rocks reveal that Earth's magnetic field has reversed its polarity hundreds of times throughout geological history. During these reversals, the field weakens dramatically and may even disappear entirely for thousands of years before re-establishing itself with opposite polarity. North becomes south, south becomes north, yet the dynamo continues operating according to the same physical principles. Computer simulations of core dynamics show that these reversals result from chaotic interactions between multiple convection cells, creating complex feedback loops that can flip the entire magnetic configuration. The system exhibits what mathematicians call sensitive dependence on initial conditions. Tiny changes in core flow patterns can trigger global magnetic reorganization. The magnetic field varies in strength and orientation over time scales ranging from seconds to millions of years. Solar storms can compress the magnetosphere and induce electrical currents in the core, creating temporary fluctuations in field intensity. Seasonal changes in solar heating affect atmospheric dynamics, which couple to the magnetosphere and influence core convection patterns. Even the gravitational pull of the moon and planets creates subtle tidal forces that affect liquid metal flow deep within the Earth. The core responds to all these influences while maintaining its primary function, protecting the surface environment from the harsh radiation of space. The mystery that puzzles planetary scientists is how Earth's core maintains such precise operating conditions. Too small and insufficient gravitational energy would be available to power convection. Too large and excessive pressure would prevent the formation of a liquid outer core. The iron content must fall within narrow limits. Too much creates a core so massive that it disrupts surface tectonics. Too little fails to generate adequate magnetic shielding. Even the sulfur content, which affects the melting temperature of iron alloys, must be precisely calibrated to maintain the solid-liquid boundary at the correct depth. Every parameter seems fine-tuned to sustain the magnetic dynamo that makes complex surface chemistry possible. Only took 50 million years to build a planetary dynamo that would operate for billions more. Yet, the precision required for this cosmic engineering project exceeds anything human technology has achieved. The core continues its patient work, generating invisible fields that extend far into space, creating the protective envelope within which life will eventually flourish. Deep beneath continents and oceans, liquid iron swirls in patterns too complex for complete mathematical description, following the same physical laws that govern the behavior of charged particles in laboratory experiments, yet scaled up to planetary dimensions and powered by the fundamental forces that shape the universe itself. Earth settles into its orbital groove with the precision of a planetary timepiece. The distance from the Sun, 149.6 million kilometers, appears unremarkable until compared to the narrow band where liquid water can exist. Venus orbits just 28% closer to the Sun, yet surface temperatures there reach 460 degrees Celsius, hot enough to melt lead. Mars lies only 52% farther out, but averages minus 63 degrees Celsius, cold enough that carbon dioxide freezes from the atmosphere during winter. Between these extremes, Earth occupies a zone so narrow that a 5% change in either direction would eliminate the possibility of surface oceans. The orbital mechanics follow Kepler's laws with mathematical exactitude. Earth travels fastest when closest to the Sun in early January, reaching 30.3 kilometers per second in its elliptical dance around the stellar furnace. 6 months later, at maximum distance, orbital velocity drops to 29.3 kilometers per second. This seemingly small difference, just 3%, creates seasonal variations in solar heating that help stabilize global climate. The planet receives 7% more sunlight during southern hemisphere summer than northern hemisphere summer, an asymmetry that moderates temperature extremes and prevents runaway ice ages. Astronomers measuring the orbits of extrasolar planets discover that most exist in highly elliptical paths that carry them alternately close to and far from their parent stars. These worlds experience temperature swings of hundreds of degrees as they follow their stretched orbits through space. Earth's eccentricity, the measure of how much an orbit deviates from a perfect circle, remains remarkably low at just 1.7%. This near-circular path ensures that seasonal variations depend primarily on axial tilt rather than changing distance from the Sun, creating stable climate patterns that persist for millions of years. The gravitational influence of Jupiter plays a crucial role in maintaining Earth's stable orbit. The massive planet, containing more mass than all other planets combined, acts as a cosmic vacuum cleaner that sweeps potentially dangerous asteroids and comets from the inner solar system. Jupiter's gravity also prevents Earth's orbit from becoming significantly more elliptical over geological timescales. Computer simulations of solar system dynamics show that without Jupiter's stabilizing presence, Earth's eccentricity would vary chaotically, sometimes reaching values high enough to boil the oceans or freeze them solid. The gas giant maintains its protective role through gravitational resonances, so precise that planetary scientists describe them as a celestial clockwork mechanism. Earth's position in the solar system also places it within what astronomers call the galactic habitable zone. The solar system orbits the center of the Milky Way galaxy at a distance of 26,000 light-years, completing one revolution every 225 million years. This location avoids the galaxy's inner regions, where frequent supernovae would sterilize planetary surfaces with lethal radiation, while staying clear of the outer spiral arms, where heavy element abundances remain too low to form rocky planets. The galactic orbit follows a nearly circular path that keeps the solar system in regions of space with relatively stable conditions for billions of years. The Sun itself exhibits remarkable stability compared to most stars of similar mass and age. Solar luminosity varies by less than 0.1% over decades, while many other stars show brightness fluctuations of several percent or more. This consistency results from the Sun's internal structure and rotation rate, both of which affect the efficiency of nuclear fusion in the stellar core. Stars that rotate faster or have different chemical compositions often display more variable energy output, creating challenging conditions for planetary climates. Earth benefits from a parent star whose energy production follows predictable patterns that permit long-term climate stability. The distance between Earth and Sun determines not just temperature, but also the intensity of ultraviolet radiation reaching the planet's surface. Too much UV light destroys organic molecules and damages the genetic material of living organisms. Too little prevents the photochemical reactions that produce ozone and other atmospheric compounds essential for life. Earth receives approximately 1,300 watts of solar energy per square meter at the top of the atmosphere, enough to drive weather systems and ocean currents, but not so much that water molecules dissociate and hydrogen escapes to space. The balance requires precise calibration of stellar luminosity, planetary distance, and atmospheric composition. Scientists studying climate models find that Earth's current orbital configuration provides optimal conditions for ice age cycles driven by Milankovitch variations. Changes in Earth's axial tilt, orbital eccentricity, and the timing of closest approach to the Sun combine to create climate oscillations with periods of approximately 21,000, 41,000, and 100,000 years. These cycles help prevent the planet from settling into permanent icehouse or greenhouse states by providing natural climate variability that drives evolutionary adaptation and maintains biogeochemical cycling. The orbital parameters seem precisely tuned to generate enough climate change to prevent stagnation without creating catastrophic instability. The habitable zone around the Sun is not fixed, but migrates outward as stellar luminosity gradually increases with age. When life first appeared on Earth 4 billion years ago, the Sun was approximately 25% dimmer than today, yet the planet maintained liquid water through enhanced greenhouse warming. As the Sun brightens over the coming billion years, Earth will eventually become too hot for life unless atmospheric greenhouse gases decrease proportionally. The planet must maintain a delicate balance between stellar heating and atmospheric cooling throughout its entire history, requiring continuous adjustment of greenhouse gas concentrations over geological timescales. Measurements of other planetary systems reveal how unusual Earth's orbital characteristics actually are. Most exoplanets discovered so far either orbit very close to their stars, completing revolutions in days rather than years, or follow highly eccentric paths that create extreme seasonal variations. The combination of a nearly circular orbit, optimal distance from a stable star, and protection by a massive outer planet appears to be relatively rare in the galaxy. Earth exists in a cosmic sweet spot that required billions of years of planetary migration and gravitational sculpting to achieve. The mystery that intrigues planetary scientists is how Earth maintained its precise orbital distance despite the gravitational perturbations that have affected the solar system throughout its history. Close encounters with passing stars, the gravitational influence of the outer planets, and even the solar wind all create forces that could potentially alter Earth's orbit over geological time. Yet the planet has remained within the habitable zone for over 4 billion years, never straying close enough to the Sun to trigger a runaway greenhouse effect or far enough away to freeze permanently. The orbital stability seems almost too perfect to result from chance alone. Tidal forces from the Moon also contribute to Earth's orbital stability by gradually slowing the planet's rotation and transferring angular momentum to the lunar orbit. This process, which continues at a rate of about 2 milliseconds per century, helps maintain the stable day length and seasonal patterns that characterize Earth's climate. Without tidal dissipation, the planet would rotate much faster, creating more extreme weather patterns and making the development of complex life more difficult. The Earth-Moon system acts as a coupled oscillator that naturally seeks configurations of minimum energy and maximum stability, only took 4.5 billion years to fine-tune an orbit that permits liquid water, moderate seasons, and protection from cosmic hazards. Yet the precision required exceeds the accuracy of the most sophisticated navigation systems human technology has devised. Earth continues its ancient journey around the Sun, following the same elliptical path that has carried it through ice ages and warm periods, mass extinctions and evolutionary radiations, always maintaining the delicate balance between fire and ice that makes life possible in this particular corner of the cosmos. 4.5 billion years ago, something the size of Mars hurtles through the inner solar system on a collision course with the young Earth. Astronomers call this hypothetical impactor Theia, after the Greek Titaness who gave birth to the moon goddess Selene. The object approaches at 11 kilometers per second, not the head-on catastrophe that would shatter both worlds, but a glancing blow struck at precisely the angle needed to excavate material from Earth's mantle while preserving the planet's iron core. The timing, velocity, and trajectory align with such precision that planetary scientists struggle to explain how random gravitational interactions could produce such an architecturally perfect collision. The impact occurs when Earth has grown to roughly 90% of its current mass, but still glows red-hot from the energy of formation. Theia strikes the planet's southeastern hemisphere at a 45-degree angle, delivering a blow equivalent to 100 million billion tons of TNT more energy than the Sun produces in a week, concentrated into a few hours of cosmic violence. The collision vaporizes both Theia's rocky mantle and a significant portion of Earth's outer layers, creating a disk of molten debris that extends beyond the current orbit of the Moon. Yet this apparent catastrophe serves a deeper architectural purpose. The debris disk condenses with remarkable efficiency over the following centuries. Rocky material, still molten from the heat of impact, begins to clump under its own gravity. The process follows the same accretionary principles that built the planets themselves, but accelerated by the proximity of Earth's gravitational field. Within 1,000 years, an instant in geological terms, most of the debris has coalesced into a single body orbiting 20,000 kilometers above Earth's surface. The new Moon forms from the lighter silicate materials blasted from both planets' mantles, while the denser iron from Theia's core merges with Earth's metallic center. This origin explains the Moon's unusual composition and the Earth-Moon system's anomalous properties. The Moon contains almost no iron core relative to its size, unlike every other large body in the solar system. Its rocks match Earth's mantle composition so precisely that isotopic analysis cannot distinguish between lunar and terrestrial samples. The system's total angular momentum exceeds what planetary formation models predict, requiring an external source of rotational energy. Only a giant impact can account for these characteristics, yet the collision parameters must fall within extremely narrow ranges to produce the observed results. The newly formed Moon begins its gravitational work immediately. At 20 times closer than its current distance, the satellite raises tides on the molten Earth that tower hundreds of meters high. These massive liquid bulges create internal friction that dissipates orbital energy, causing the Moon to spiral slowly outward while transferring angular momentum from Earth's rotation to the lunar orbit. The process follows precise mathematical relationships derived from celestial mechanics. Energy and angular momentum must be conserved. Tidal forces decrease as the inverse cube of distance, and orbital periods increase according to Kepler's third law. As the Moon recedes, Earth's rotation slows from an initial period of perhaps 5 hours to the current 24-hour day. This deceleration occurs gradually over billions of years, allowing the planet's climate and biological systems to adapt to changing day lengths. Computer simulations show that without this tidal braking, Earth would still rotate every 6 to 8 hours, creating atmospheric dynamics so violent that weather patterns would remain chaotic. The lunar influence provides the long, stable days that permit complex atmospheric circulation and moderate seasonal variations. The Moon's gravitational field also stabilizes Earth's axial tilt at 23.5 degrees from vertical. This obliquity creates the seasonal variations that drive oceanic and atmospheric circulation while preventing the dramatic climate swings that would result from larger tilts. Mars, lacking a large moon, experiences chaotic variations in obliquity ranging from 0 to 60 degrees over millions of years, causing extreme climate instability. Venus rotates nearly upside down, creating minimal seasonal variation but extreme temperature differences between day and night. Earth's tilt remains remarkably constant, varying by only about 2 degrees over 41,000-year cycles. The lunar orbit itself exhibits properties that seem almost intentionally designed for Earth's benefit. The Moon's distance varies by only about 12% from its average value, much less than the highly elliptical orbits characterizing most satellite systems. This near-circular path ensures that tidal forces remain relatively constant rather than varying dramatically throughout each month. The orbital plane tilts just 5 degrees from Earth's orbital plane around the Sun, preventing excessive perturbations from solar gravity that could destabilize the satellite's motion over geological time. Tidal interactions between Earth and Moon create a phenomenon unique in the solar system: total solar eclipses. The Moon's apparent diameter, as seen from Earth's surface, matches the Sun's apparent size to within 1%, allowing the lunar disk to precisely cover the solar photosphere during eclipses. This remarkable coincidence results from the Moon's gradual recession from Earth. 4 billion years ago, the Moon appeared 4 times larger than the Sun and blocked the solar disk completely during eclipses. 4 billion years from now, it will appear too small to cover the Sun entirely. Earth experiences perfect eclipses only during this brief window of cosmic time. The Apollo missions reveal that the Moon possesses its own subtle magnetic field. Despite lacking a liquid metallic core, lunar rocks preserve evidence of ancient magnetism locked in their crystal structures, suggesting that the Moon once generated a dynamo similar to Earth's, but much weaker. This magnetic field may have provided additional protection from solar wind during the early bombardment period, helping to preserve the volatile compounds essential for life. The lunar magnetism disappeared as the small iron core solidified completely, but operated long enough to shield Earth's early atmosphere during its most vulnerable period. Studies of lunar samples show that the Moon formed in a state of complete melting, with surface temperatures exceeding 1,500 degrees Celsius. This global magma ocean differentiated over millions of years as denser materials sank toward the center and lighter minerals floated to the surface. The process created the bright highlands visible from Earth today, composed of anorthosite rock that formed as plagioclase feldspar crystals accumulated at the top of the cooling magma ocean. The dark maria, visible as the "man in the moon" pattern, represent later impacts that punched through the crust and filled with basaltic lava flows. The Moon's gravitational influence extends far beyond tidal effects to subtle interactions that affect Earth's climate and geology over millions of years. Lunar gravity modulates the strength of Earth's gravitational field, creating variations that influence atmospheric circulation patterns and ocean currents. The Moon's orbital motion affects the planet's rotation rate through complex resonances that operate over geological timescales. Even the rate of continental drift may be influenced by lunar tidal forces that stress the Earth's crust and affect the convection patterns driving plate tectonics. The mystery that captivates planetary scientists is how the Theia impact achieved such precise results. The impactor must have been exactly the right size too small, and insufficient material would have been ejected to form a large moon. Too large, and both planets would have been destroyed. The collision angle must have been nearly perfect, too direct, and both cores would have merged immediately. Too oblique, and the impactor would have bounced off into space. The velocity must have fallen within narrow limits to excavate mantle material without completely disrupting the planet. Every parameter seems fine-tuned to produce the Earth-Moon system that exists today. Computer models of the impact event require hundreds of assumptions about initial conditions, material properties, and physical processes that operated during the collision. Small changes in any parameter can dramatically alter the outcome, either preventing moon formation entirely or creating satellite systems unlike what we observe. The probability of achieving the precise conditions needed appears vanishingly small when considered as a random event. Yet here orbits the evidence, a moon that stabilizes Earth's climate, moderates its rotation, and creates the tidal forces that may have been essential for the origin of life. Only took a few hours to reshape two worlds and engineer the Earth-Moon system that has operated with clockwork precision for 4.5 billion years. Yet the collision required such exact timing and geometry that some scientists wonder whether cosmic architecture follows principles beyond simple gravitational dynamics. The moon continues its slow spiral away from Earth, still influencing tides and seasons, still stabilizing the planet's axial tilt, still marking time with the same orbital mechanics that governed its birth in the fires of the early solar system. In the aftermath of the Great Impact, Earth begins the delicate process of atmospheric construction. The collision that formed the moon vaporized much of the planet's early atmosphere, stripping away hydrogen and helium that had accumulated during formation. What remains is a thin envelope of rock vapor and metallic gases glowing white-hot above the molten surface. Yet, within this apparent devastation lies the foundation for something unprecedented. The first atmosphere in the solar system capable of supporting complex chemistry, and, eventually, life itself. Volcanic outgassing provides the primary building materials for Earth's new atmospheric assembly. Thousands of volcanoes puncture the cooling crust, each one a factory releasing precisely calibrated mixtures of water vapor, carbon dioxide, sulfur compounds, and nitrogen. The ratios follow thermodynamic principles governing the solubility of gases in molten rock at specific temperatures and pressures. Water vapor dominates the early releases because it dissolves readily in magma and vaporizes completely at surface temperatures exceeding 800 degrees Celsius. Carbon dioxide emerges in smaller but significant quantities, providing the greenhouse warming needed to prevent total atmospheric collapse. The outgassing process operates with industrial-scale efficiency over millions of years. Each volcanic eruption contributes to the growing atmospheric inventory according to the chemical composition of the underlying mantle. Basaltic lavas release more water and carbon dioxide than granitic melts, while ultramafic rocks contribute additional hydrogen and methane. The planetary degassing follows predictable patterns based on the distribution of radioactive elements that provide internal heating and the convection patterns that bring molten material to the surface. No conscious design guides this process, yet the resulting atmospheric composition falls within narrow ranges compatible with surface liquid water. Water vapor condenses as surface temperatures drop below 100 degrees Celsius, creating Earth's first rainfall after millions of years of steam atmosphere conditions. The transition occurs gradually as volcanic activity decreases and heat from the impact. Generated magma ocean slowly radiates into space. When condensation finally begins, it triggers a positive feedback loop. Water vapor, a potent greenhouse gas, decreases in concentration as it condenses, allowing further cooling and more condensation. Within perhaps 100,000 years, Torrential rains wash the remaining water from the atmosphere and begin filling the first ocean basins. The early atmosphere contains virtually no free oxygen, creating chemical conditions unlike anything in Earth's modern environment. Carbon dioxide concentrations may have reached levels 100 times higher than today, providing sufficient greenhouse warming to maintain liquid water despite the sun's lower luminosity 4 billion years ago. Methane, hydrogen sulfide, and ammonia contribute additional greenhouse effects while participating in complex photochemical reactions driven by ultraviolet radiation from the young sun. These reducing conditions prove essential for the organic chemistry that will eventually produce the first living organisms. Atmospheric pressure during this period remains uncertain, but probably exceeded 10 times the current value due to the massive volcanic outgassing. Under these conditions, water can exist as a liquid at temperatures well above 100 degrees Celsius, expanding the range of environments suitable for chemical evolution. The thick atmosphere also provides protection from the intense bombardment that continues for several 100 million years after Earth's formation. Incoming asteroids and comets must penetrate dense atmospheric layers that burn away smaller objects while slowing larger ones enough to prevent complete surface sterilization. The composition gradually evolves as chemical reactions between atmospheric gases and surface rocks reach equilibrium. Carbon dioxide dissolves in the growing oceans, forming carbonic acid that weathers silicate minerals and removes atmospheric carbon through limestone precipitation. This carbonate-silicate cycle creates a natural thermostat that regulates planetary temperature over geological timescales. When surface temperatures rise, weathering accelerates and removes more carbon dioxide from the atmosphere, causing cooling. When temperatures fall, reduced weathering allows volcanic carbon dioxide to accumulate and warm the planet through enhanced greenhouse effects. Nitrogen accumulates as a major atmospheric constituent because it remains chemically inert under most surface conditions. Volcanic outgassing releases nitrogen compounds that decompose in the hot atmosphere, leaving behind molecular nitrogen that cannot easily react with surface materials or escape to space. This gas provides atmospheric mass and pressure while remaining largely invisible to the chemical processes that affect other atmospheric constituents. The nitrogen inventory grows steadily through geological time as continued volcanism adds more to the atmospheric reservoir. Solar radiation drives photochemical reactions that create trace amounts of more complex molecules in the upper atmosphere. Ultraviolet light splits water molecules into hydrogen and oxygen atoms, though most of the hydrogen escapes to space while oxygen reacts with surface materials or dissolved iron in the oceans. Carbon dioxide and methane undergo similar photodissociation reactions that produce carbon monoxide, formaldehyde, and other organic compounds. These processes operate at molecular scales, yet affect the atmospheric composition of an entire planet, demonstrating how quantum mechanical principles scale up to influence global environments. The young sun emits much higher levels of ultraviolet radiation than today due to its more active magnetic field and frequent solar flares. This intense UV flux drives atmospheric chemistry, but also poses challenges for any organic molecules that might form at the surface. Water vapor in the upper atmosphere absorbs some ultraviolet wavelengths, providing partial protection, while the lack of ozone allows other harmful radiation to reach the surface unimpeded. The balance between beneficial photochemistry and destructive radiation creates a narrow window of conditions suitable for organic synthesis. Impact delivery supplements volcanic outgassing by bringing additional volatile compounds from the outer solar system. Comets and carbonaceous asteroids contain water, organic molecules, and rare gases that add to Earth's atmospheric inventory. The isotopic composition of noble gases in Earth's atmosphere suggests that significant fractions came from cometary sources rather than volcanic outgassing alone. These impacts also deliver preformed organic compounds, including amino acids, nucleotide bases, and complex hydrocarbons that provide raw materials for biological evolution. Atmospheric escape processes operate continuously but selectively, removing different gases at different rates. Hydrogen, the lightest element, escapes most readily through thermal processes in the upper atmosphere, where solar heating provides sufficient kinetic energy for molecules to exceed escape velocity. Heavier gases like carbon dioxide and water vapor escape more slowly through non-thermal processes such as solar wind sputtering and charge exchange reactions. The net result is gradual atmospheric evolution toward compositions enriched in heavier elements that cannot easily escape to space. The early atmosphere lacks the complex layered structure that characterizes modern Earth's air. No stratospheric ozone layer exists to absorb ultraviolet radiation and create temperature inversions. No jet streams form because the rapid rotation rate and uniform surface heating produce different circulation patterns than those observed today. Weather systems probably consist of massive convective storms driven by the high atmospheric pressure and greenhouse heating, creating turbulent mixing that homogenizes atmospheric composition more effectively than current circulation patterns. The mystery that puzzles atmospheric scientists is how Earth retained a substantial atmosphere while similar planets lost theirs entirely. Venus developed a runaway greenhouse effect that boiled away its water and left behind a crushing carbon dioxide atmosphere 9 times denser than Earth's. Mars lost most of its atmosphere to space, leaving behind a thin envelope barely 1% as dense as Earth's current air. Both planets started with atmospheric compositions probably similar to early Earth's, yet only Earth maintained the delicate balance between atmospheric retention and climate stability required for long-term habitability. Magnetic field protection plays a crucial role in atmospheric retention by deflecting solar wind particles that would otherwise strip away atmospheric gases. Earth's magnetic dynamo begins operating within 50 million years of the planet's formation, providing this essential shield during the critical early period when atmospheric escape rates remain highest. Planets without magnetic fields, like Mars and Venus, experience much higher escape rates that can remove entire atmospheres over billions of years. Earth's magnetic protection seems precisely calibrated to preserve atmospheric mass while allowing gradual evolution toward compositions suitable for life. Only took a few 100 million years to construct an atmosphere capable of supporting liquid water and complex chemistry. Yet the process required precise coordination between volcanic outgassing rates, impact delivery, atmospheric escape, and magnetic field protection. The resulting atmospheric composition provided exactly the greenhouse warming needed to compensate for lower solar luminosity while maintaining chemical conditions suitable for organic synthesis. Earth's first atmosphere represented a masterpiece of planetary engineering that set the stage for 4 billion years of biological evolution, deep beneath the cooling oceans. Earth begins constructing its most sophisticated engineering project, a system of moving plates that will regulate planetary temperature for billions of years. The process starts with thermal convection in the mantle, where hot rock rises from the core mantle boundary and cold material sinks from the surface. These circulation patterns follow fluid dynamics principles that operate in everything from boiling water to stellar atmospheres. Yet when scaled to planetary dimensions, they create a geological machine of extraordinary precision and complexity. The mantle convects because radioactive decay of uranium, thorium, and potassium generates heat faster than conduction can carry it to the surface. Temperature differences of only a few 100 degrees between the bottom and top of the mantle drive circulation patterns that transport material over distances of thousands of kilometers. The viscosity of hot rock, about 1 billion trillion times thicker than water, allows convection to operate over geological timescales while maintaining the structural integrity needed to support continents and ocean basins above. Rising mantle plumes create the first volcanic islands and oceanic ridges where new crustal material forms through partial melting of ascending rock. The chemistry follows precise relationships between temperature, pressure, and mineral stability that determine which elements concentrate in the melt and which remain in the solid residue. Basaltic magmas rich in magnesium and iron crystallize to form the oceanic crust, while more evolved compositions create the granitic rocks that will become the cores of continents. Each magma batch represents a sophisticated chemical separation process that sorts elements according to their atomic properties and thermodynamic behavior. The newly formed oceanic crust spreads away from volcanic ridges at rates measured in centimeters per year, about as fast as fingernails grow. This seemingly slow motion accumulates over millions of years to transport crustal material across entire ocean basins. Magnetic minerals in the cooling lava record the direction of Earth's magnetic field when they crystallized, creating a tape recorder of ancient magnetic reversals preserved in the ocean floor. The magnetic stripes provide compelling evidence that seafloor spreading operates with clockwork regularity over geological time. As oceanic plates move away from spreading centers, they cool and become denser than the underlying mantle. Eventually, usually after 50 to 100 million years, the cold oceanic lithosphere becomes dense enough to sink back into the mantle at subduction zones. The process operates according to simple buoyancy principles. Dense materials sink while light materials rise, yet creates one of the most complex geological environments on Earth. Subduction zones generate the planet's most powerful earthquakes, explosive volcanic eruptions, and towering mountain ranges. The subduction process recycles oceanic crust back into the mantle with remarkable efficiency. Water trapped in sediments and altered oceanic rocks lowers the melting temperature of surrounding mantle material, generating magmas that rise to form volcanic arcs. These island chains and continental volcanic ranges create some of Earth's most spectacular landscapes, while serving essential functions in global geochemical cycles. Subduction zones remove carbon dioxide from the atmosphere by carrying carbonate minerals into the mantle, where high temperatures decompose them and release carbon dioxide through volcanic outgassing. Continental crust forms through a multi-stage process that concentrates incompatible elements into increasingly silica-rich compositions. Basaltic magmas generated at oceanic ridges undergo fractional crystallization as they cool, leaving behind evolved melts enriched in silicon, aluminum, and alkali metals. These intermediate compositions react with seawater and undergo additional melting and crystallization cycles that produce the granitic rocks characteristic of continental crust. The entire process acts as a planetary distillation system that separates elements according to their geochemical behavior. The thickness and composition of continental crust create buoyancy that prevents it from subducting back into the mantle. Like icebergs floating on water, continents ride on the denser oceanic plates and mantle materials that surround them. This buoyancy ensures that once formed, continental crust persists for billions of years, while oceanic crust recycles completely every few 100 million years. The asymmetry between permanent continents and temporary ocean basins creates the geological framework for plate tectonics to operate over Earth's entire history. Plate boundaries develop along zones of mechanical weakness where different types of lithosphere meet. Transform faults allow plates to slide past each other horizontally, accommodating the spherical geometry of plate motion on Earth's curved surface. Divergent boundaries create new oceanic crust through seafloor spreading, while convergent boundaries consume old crust through subduction. The network of plate boundaries forms a continuous system that encircles the globe, dividing Earth's surface into a dozen major plates and numerous smaller fragments. The driving forces for plate tectonics include both push and pull mechanisms operating at different parts of the system. Ridge push results from gravitational sliding of oceanic plates down the slopes created by elevated mid-ocean ridges. Slab pull occurs when dense oceanic lithosphere sinks into the mantle and drags the rest of the plate behind it. Mantle convection provides additional driving forces through viscous coupling between moving mantle material and the overlying plates. Computer models suggest that slab pull provides the dominant driving force, while ridge push and convection contribute smaller but significant amounts. The speeds of plate motion vary from less than 1 centimeter per year to more than 10 centimeters per year, depending on the balance between driving and resisting forces. Faster-moving plates typically have larger proportions of their boundaries occupied by subduction zones, where slab pull operates most effectively. Slower plates often have extensive continental margins that resist motion through their greater thickness and lower density. The global average spreading rate remains remarkably constant over geological time, suggesting that plate tectonics operates in a steady-state configuration maintained by thermal and gravitational forces. Plate tectonics creates a global thermostat system that regulates Earth's surface temperature through the carbonate-silicate cycle. When surface temperatures rise, enhanced weathering of silicate rocks removes more carbon dioxide from the atmosphere, causing cooling. When temperatures fall, reduced weathering allows volcanic carbon dioxide to accumulate and warm the planet. The feedback operates over timescales of hundreds of thousands to millions of years, slow enough to permit climate evolution, but fast enough to prevent runaway greenhouse or icehouse conditions. The cycling of water between surface reservoirs and the mantle through subduction and volcanic outgassing maintains the global water budget over geological time. Hydrated minerals in subducting oceanic crust carry water into the mantle, where it affects melting processes and eventually returns to the surface through volcanic emissions. This deep water cycle operates in parallel with the familiar surface water cycle of evaporation and precipitation, creating a planetary water management system that maintains ocean levels within narrow bounds for billions of years. The generation of continental crust through plate tectonic processes creates the elevated land masses essential for complex surface environments. Without continents, Earth would be covered by a global ocean several kilometers deep, eliminating the shallow seas, river systems, and terrestrial environments that prove crucial for biological evolution. The formation of supercontinents through plate collision creates massive mountain ranges that affect global climate patterns, while their subsequent breakup redistributes continental fragments and creates new ocean basins. The mystery that intrigues geologists is why plate tectonics operates only on Earth among the terrestrial planets. Venus has a similar size and composition, but shows no evidence of current plate motion, instead experiencing episodic global resurfacing events. Mars appears to have had brief periods of tectonic activity early in its history, but lacks the driving forces to maintain long-term plate motion. Earth's plate tectonic system requires a precise combination of planetary mass, thermal structure, and surface conditions that other worlds apparently lack. The presence of liquid water plays a crucial role in lubricating plate boundaries and weakening the lithosphere through hydration reactions. Without water, rocks remain too strong to permit the easy motion of large crustal blocks required for plate tectonics. The magnetic field may also contribute by protecting atmospheric water from solar wind stripping, ensuring that sufficient water remains available for geological processes. Even the Moon's tidal forces may help drive plate motion by creating stress variations that facilitate movement along fault systems. Only took a few 100 million years to establish the plate tectonic system that has operated continuously for over 3 billion years. Yet the process required precise coordination between mantle convection, crustal formation, and surface water cycles. The resulting geological machine creates and destroys ocean basins, builds and erodes mountain ranges, and regulates planetary climate through geochemical feedbacks that maintain surface conditions suitable for life. Deep beneath the continents and oceans, the slow dance of plate tectonics continues, following the same physical principles that have shaped Earth's surface since the earliest days of its geological evolution. 2.5 billion years ago, microscopic organisms floating in shallow seas begin the most ambitious atmospheric engineering project in Earth's history. Cyanobacteria, blue-green algae no larger than the period at the end of this sentence, develop the biochemical machinery to split water molecules using nothing more than sunlight and carbon dioxide. The process they invent, oxygenic photosynthesis, will fundamentally transform the planet's chemistry and atmosphere over the following 2 billion years, creating conditions that make complex life possible while simultaneously triggering the most catastrophic extinction event in Earth's geological record. The photosynthetic apparatus operates with quantum mechanical precision that exceeds the efficiency of human-designed solar cells. Chlorophyll molecules absorb photons and transfer their energy through a cascade of electron transport reactions that ultimately extract hydrogen atoms from water molecules. The leftover oxygen atoms combine to form molecular oxygen gas that bubbles out of the cell and escapes into the surrounding water. Each photosynthetic reaction requires exactly 4 photons to liberate one oxygen molecule, following stoichiometric relationships as precise as any industrial chemical process. The biochemistry follows thermodynamic principles that make the process barely feasible under Earth's surface conditions. Splitting water molecules requires substantial energy input because the bonds between hydrogen and oxygen atoms are among the strongest in chemistry. Only the most energetic photons in sunlight, those in the blue and red wavelengths, carry sufficient energy to drive the reaction. Cyanobacteria evolve pigment systems that capture these high-energy photons with near-perfect efficiency while reflecting the less useful green wavelengths that give them their characteristic color. Oxygen production begins slowly as the first cyanobacterial populations establish themselves in shallow marine environments where sunlight penetrates to the sea floor. The initial oxygen output dissolves immediately in seawater and reacts with dissolved iron to form rust-colored precipitates that settle to the ocean bottom. These banded iron formations accumulate for hundreds of millions of years, creating geological records of the earliest biological oxygen production. Each thin layer represents seasonal variations in photosynthetic activity, providing evidence that even the earliest oxygen-producing organisms followed predictable annual cycles. The ocean chemistry during this period differs dramatically from modern seawater because dissolved iron concentrations exceed current levels by factors of thousands. Under the reducing conditions that prevailed before oxygenic photosynthesis, iron remains soluble as ferrous compounds that give seawater a greenish tint. As oxygen levels gradually increase, this dissolved iron precipitates as ferric oxide minerals, creating the distinctive red and black striped patterns visible in banded iron formations throughout the geological record. The process removes virtually all dissolved iron from the oceans over several 100 million years. Atmospheric oxygen concentrations remain negligible for the first billion years of cyanobacterial evolution because all the biologically produced oxygen reacts with reduced materials at Earth's surface. Volcanic gases contain hydrogen sulfide, carbon monoxide, and methane that consume oxygen through combustion reactions. Weathering of continental rocks exposes sulfide and iron minerals that oxidize rapidly when exposed to even trace amounts of oxygen. The early atmosphere and surface act as an enormous sink that absorbs biological oxygen production without allowing significant accumulation in the air. The Great Oxidation Event begins approximately 2.4 billion years ago, when oxygen sinks finally becomes saturated and can no longer absorb all the biologically produced oxygen. Atmospheric oxygen concentrations rise from essentially 0 to perhaps 1% of current levels. Within a few million years, a rapid transition that represents one of the most dramatic environmental changes in Earth's history. The oxygen rise triggers a cascade of chemical reactions that permanently alter the composition of the atmosphere, oceans, and continental surfaces. The oxygen increase proves lethal to most existing life forms because molecular oxygen acts as a powerful cellular poison for organisms that evolved under reducing conditions. Oxygen reacts with organic molecules to produce highly reactive free radicals that damage cell membranes, proteins, and genetic material. Most archaea and bacteria lack the biochemical defenses needed to survive in oxygenated environments, leading to massive extinctions that eliminate entire lineages of microorganisms. Scientists call this the Great Oxidation Catastrophe, because it represents the first major extinction event caused by biological activity rather than physical disasters. Methane concentrations in the atmosphere drop precipitously as oxygen levels rise because the two gases react spontaneously to form carbon dioxide and water vapor. Methane had provided significant greenhouse warming during the Archean eon, helping to maintain moderate surface temperatures despite the sun's lower luminosity. The methane collapse causes global cooling that may have triggered the first snowball Earth glaciation around 2.4 billion years ago. Ice sheets advance from the poles toward the equator, covering most of the planet's surface in a frozen layer several kilometers thick. The snowball Earth conditions persist for millions of years because ice reflects most incoming sunlight back to space, creating a positive feedback loop that maintains frigid temperatures even as atmospheric carbon dioxide concentrations increase through continued volcanic outgassing. Only when carbon dioxide levels reach concentrations hundreds of times higher than modern values does sufficient greenhouse warming develop to begin melting the global ice sheets. The deglaciation occurs rapidly once it begins, creating extreme climate swings between icehouse and greenhouse conditions. Surviving organisms adapt to the new oxygenated environment by developing cellular mechanisms to detoxify oxygen and harness its chemical energy for metabolism. Aerobic respiration. The process that most modern organisms use to extract energy from food becomes possible only after oxygen accumulates to significant levels in the atmosphere. This metabolic pathway releases approximately 20 times more energy per glucose molecule than anaerobic fermentation, providing the energy budget needed to support larger and more complex cells. The evolution of eukaryotic cells organisms with nuclei and internal organelles occurs during or shortly after the Great Oxidation Event, possibly as a direct result of the new oxygen-rich environment. Mitochondria. The organelles that perform aerobic respiration in eukaryotic cells appear to be descended from aerobic bacteria that took up residence inside larger host cells. This endosymbiotic relationship provides protection for the aerobic bacteria while supplying the host cell with efficient energy production, creating a partnership that proves essential for the evolution of complex multicellular life. Ozone formation in the upper atmosphere provides crucial protection from ultraviolet radiation as oxygen concentrations continue to increase. Molecular oxygen absorbs high-energy solar photons and splits into individual oxygen atoms, which then recombine with other oxygen molecules to form ozone. The ozone layer filters out the most harmful ultraviolet wavelengths that would otherwise sterilize Earth's surface, allowing life to colonize shallow waters and eventually terrestrial environments. The ozone shield develops automatically as a byproduct of oxygen accumulation, requiring no additional biological innovation. The oxidation of continental surfaces accelerates as atmospheric oxygen levels rise, creating new types of soils and sedimentary rocks enriched in oxidized iron and sulfur compounds. Red beds, sedimentary formations colored by iron oxide minerals, appear in the geological record for the first time during the Great Oxidation Event and become increasingly common in younger rocks. These continental red beds provide evidence that oxygen concentrations reached levels sufficient to oxidize surface materials, even in terrestrial environments far from photosynthetic organisms. Atmospheric oxygen concentrations stabilize at levels well below modern values for over 1 billion years after the initial rise, suggesting that biological and geological processes reach a new equilibrium state. Oxygen production by cyanobacteria balances consumption through organic matter decay, rock weathering, and reaction with volcanic gases. This steady-state condition maintains oxygen at levels sufficient to support aerobic metabolism while preventing the atmospheric concentrations from rising high enough to interfere with other essential biogeochemical cycles. The mystery that puzzles geochemists is how cyanobacteria evolved the complex biochemical machinery needed for oxygenic photosynthesis. The process requires coordination between dozens of proteins, metal cofactors, and organic molecules that must work together with extraordinary precision. The slightest malfunction in any component can shut down the entire system or produce toxic byproducts that kill the cell. The evolution of such complexity seems to require intermediate steps that would provide selective advantages. Yet no known organisms use simplified versions of the photosynthetic apparatus. The timing of the Great Oxidation Event also coincides with other major changes in Earth's surface environment, including the stabilization of continental crust, the development of sulfur isotope fractionation patterns, and the first appearance of certain trace fossils. Whether these changes represent causes or consequences of atmospheric oxygenation remains uncertain, but their coordination suggests that the Great Oxidation Event involved interactions between biological, geological, and atmospheric processes operating at global scales. Only took 2 billion years for microscopic organisms to engineer an atmosphere capable of supporting complex life. Yet the precision required for this biological project exceeded anything human technology has achieved. Cyanobacteria continue their ancient work today, producing oxygen through the same photosynthetic reactions that transformed Earth's early atmosphere, following biochemical pathways that operate with the reliability of molecular machines designed to maintain planetary habitability for billions of years. 700 million years ago, Earth enters a period of climate experimentation so extreme that ice sheets advance from the poles until they meet at the equator, creating a planet that resembles a giant snowball spinning through space. The Neoproterozoic glaciations represent the most severe climate crisis in Earth's recorded history. Yet these frozen episodes serve as crucial quality control tests for planetary systems that will ultimately prove essential for the evolution of complex life. The ice ages operate according to feedback mechanisms so precise that they regulate atmospheric composition, ocean chemistry, and continental weathering with the efficiency of a global thermostat system. The snowball conditions develop when several factors align to reduce Earth's ability to absorb solar radiation. Continental drift assembles most land masses near the equator, where tropical weathering accelerates the breakdown of silicate rocks and removes carbon dioxide from the atmosphere through carbonate formation. volcanic activity decreases temporarily, reducing the supply of greenhouse gases that normally help maintain moderate temperatures. Ocean circulation patterns change as continental configurations alter the flow of warm water from equatorial to polar regions. Each factor alone might cause modest cooling, but their combination triggers catastrophic climate collapse. Ice albedo feedback amplifies the initial cooling through a runaway process that operates with mathematical inevitability. Fresh snow reflects 90% of incoming sunlight back to space, compared to only 10% reflection from dark ocean water or bare soil. As temperatures drop and ice coverage expands, more solar energy reflects away from Earth's surface, causing additional cooling and further ice expansion. The positive feedback continues until ice sheets cover the entire planet, except for a narrow band of open water near the equator where geothermal heating keeps temperatures just above freezing. The frozen oceans maintain liquid water beneath several kilometers of ice through heat flow from Earth's interior, and the insulating properties of the ice cover itself. Deep ocean temperatures remain close to 4 degrees Celsius, the temperature of maximum water density, while surface ice temperatures drop to minus 40 degrees Celsius or lower. This thermal gradient drives convection in the liquid layer that transports nutrients and dissolved gases throughout the global ocean system. Life persists in these dark waters, sustained by chemosynthetic bacteria that derive energy from sulfur and iron compounds rather than sunlight. Volcanic outgassing continues throughout the snowball episodes, gradually increasing atmospheric carbon dioxide concentrations, while the frozen surface prevents removal through weathering reactions. Carbon dioxide dissolves poorly in ice compared to liquid water, allowing the gas to accumulate in the atmosphere at concentrations that eventually reach levels hundreds of times higher than modern values. The process requires millions of years because volcanic emission rates remain relatively low, but the one-way accumulation of greenhouse gases makes eventual deglaciation inevitable according to basic thermodynamics. The transition from snowball to greenhouse conditions occurs rapidly once atmospheric carbon dioxide reaches concentrations sufficient to overwhelm ice albedo feedback. Computer climate models suggest that deglaciation begins when carbon dioxide levels exceed present-day values by factors of 100 to 1,000, providing enough greenhouse warming to start melting equatorial ice. Once melting begins, it accelerates through the same albedo feedback that caused the initial freezing, but operating in reverse dark ocean water absorbs more solar energy than reflective ice, causing additional warming and further melting. The deglaciation phase creates some of the most extreme climate conditions in Earth's history, as the planet swings from completely frozen to intensely hot within a few thousand years. Surface temperatures may have exceeded 50 degrees Celsius as the massive atmospheric carbon dioxide concentrations create greenhouse warming more intense than anything experienced before or since. The hot conditions persist until enhanced weathering of newly exposed continental surfaces removes the excess carbon dioxide and returns atmospheric composition to more moderate levels. The entire cycle from snowball to greenhouse to normal climate takes approximately 10 million years. Cap carbonates, unusual limestone formations that sit directly on top of glacial deposits, provide geological evidence for the extreme chemical conditions during deglaciation. These rocks form when the highly acidic oceans, enriched in carbon dioxide from millions of years of accumulation, suddenly become supersaturated with calcium carbonate as temperatures rise and carbon dioxide solubility decreases. Massive limestone precipitation occurs rapidly across the entire planet, creating distinctive rock formations that mark the end of each snowball episode with remarkable consistency. The ocean chemistry during snowball conditions differs dramatically from anything observed in modern seas due to the isolation from atmospheric exchange and the concentration of dissolved minerals through partial freezing. Iron concentrations increase to levels not seen since the Archean Eon, as oxidized iron from continental weathering accumulates without being precipitated by reaction with atmospheric oxygen. Sulfate concentrations vary dramatically due to bacterial reduction in oxygen, poor deep waters, and the absence of river input from frozen continents. These chemical extremes create selection pressures that drive evolutionary innovation in surviving microbial communities. Isotopic signatures in rocks from snowball periods reveal that biological productivity collapsed during the glaciations but recovered rapidly during the warm intervals between ice ages. Carbon isotope ratios show minimal fractionation during snowball conditions, indicating that photosynthesis operated at very low levels beneath the ice cover. Sulfur isotopes display unusual patterns that suggest bacterial sulfate reduction proceeded through different pathways than those operating under normal marine conditions. These geochemical fingerprints provide evidence that snowball episodes represented global ecological crises that fundamentally altered biogeochemical cycles. The Neoproterozoic includes at least 2 major snowball episodes separated by tens of millions of years of more moderate climate conditions. The Sturcian glaciation occurs around 715 million years ago, while the Marinoan glaciation peaks at approximately 635 million years ago. Each episode shows similar geological signatures: glacial deposits at tropical latitudes, distinctive cap carbonates, and extreme carbon isotope excursions, suggesting that both glaciations operated through the same fundamental mechanisms despite their temporal separation. Surviving organisms develop biochemical adaptations that allow them to function under the extreme conditions that characterize snowball and post-snowball environments. Cold shock proteins help maintain cellular function at near-freezing temperatures, while heat shock proteins provide protection during the subsequent greenhouse warming. Some microorganisms evolve the ability to enter dormant states that can survive frozen conditions for millions of years, then rapidly resume metabolic activity when favorable conditions return. These adaptations prove crucial for the evolutionary radiation that follows the final snowball episode. The snowball glaciations coincide with major evolutionary innovations, including the origin of complex multicellular organisms and the development of sexual reproduction. The extreme environmental fluctuations may have accelerated evolutionary rates by creating strong selection pressures for organisms capable of surviving rapid climate change. Genetic recombination through sexual reproduction provides the variability needed to adapt quickly to changing conditions, while multicellularity allows specialization of different cell types for specific environmental challenges. Atmospheric oxygen concentrations appear to increase significantly during and after the Neoproterozoic glaciations, possibly due to enhanced organic matter burial under the ice sheets or changes in ocean circulation that affect the balance between oxygen production and consumption. Higher oxygen levels support the metabolism of larger and more active organisms, providing the energy budget needed for the evolution of animals with complex body plans and active lifestyles. The oxygen increase represents another example of how extreme climate events can drive long-term environmental changes that affect biological evolution. The mystery that puzzles climate scientists is how Earth managed to escape from snowball conditions rather than remaining permanently frozen like some of Jupiter's ice-covered moons. The delicate balance between volcanic carbon dioxide input and ice albedo feedback operates within narrow parameters that determine whether deglaciation occurs at all. Slightly lower volcanic emission rates or different continental configurations might have prevented sufficient carbon dioxide accumulation to trigger melting, leaving Earth as a permanently frozen world incapable of supporting complex life. The precise timing of the snowball glaciations also coincides with other major changes in Earth's surface environment, including the breakup of supercontinents, changes in ocean circulation patterns, and fluctuations in atmospheric composition. Whether these represent causes or consequences of the glaciations remains uncertain, but their coordination suggests that snowball episodes involved complex interactions between geological, atmospheric, and biological processes operating at global scales over millions of years. Only took a few million years to test planetary climate systems through the most extreme conditions in Earth's history. Yet the snowball glaciation served as essential quality control procedures that prepared the planet for the evolution of complex life. The ice ages demonstrated that Earth's climate system could survive catastrophic perturbations and return to habitable conditions, while the extreme environmental fluctuations drove evolutionary innovations that proved crucial for the subsequent radiation of multicellular organisms during the Ediacaran and Cambrian periods. 600 million years ago. In the warm seas that follow the final snowball Earth glaciation, life begins its first experiments with multicellular architecture. The Ediacaran biota, Earth's earliest known complex organisms, appear with the sudden precision of an assembly line coming online, their soft bodies preserving in fine-grained sediments as delicate impressions that capture anatomical details with photographic clarity. These creatures follow construction blueprints unlike anything that exists today, yet their organizational principles establish the fundamental engineering concepts that will govern biological complexity for the remainder of Earth's history. The organisms develop from single cells through controlled developmental programs that coordinate cell division, differentiation, and spatial organization with mathematical precision. Embryonic development follows genetic instructions encoded in DNA sequences that specify when and where different types of cells should form during growth. The process operates through chemical gradients and signaling molecules that create positional information within the developing organism, allowing cells to determine their location and adopt appropriate functions. No external architect guides this construction, yet the resulting body plans exhibit symmetries and proportions that follow geometric principles discovered by mathematicians millions of years later. Dickinsonia, one of the most abundant Ediacaran fossils, grows through the addition of identical segments arranged in bilateral symmetry around a central axis. Each segment contains the same internal structures repeated with modular precision, creating organisms that can reach lengths of over 1 meter while maintaining structural integrity. The segmented body plan demonstrates how biological systems solve engineering problems through repetition of proven designs rather than inventing entirely new architectures for each size increase. This principle of modular construction will later appear in arthropods, vertebrates, and other complex animal groups. The quilted construction technique used by many Ediacaran organisms represents a unique solution to the problem of maintaining three-dimensional structure without rigid skeletal support. Internal partitions divide the body cavity into chambers that can be inflated with fluid to create structural rigidity, similar to an air mattress or inflatable boat. The chamber walls follow fractal patterns that maximize surface area while minimizing material costs, creating internal architectures of surprising mathematical sophistication. This quilted design allows organisms to achieve large sizes while remaining flexible enough to bend with ocean currents. Rangeomorphs, another major group of Ediacaran organisms, exhibit fractal branching patterns that repeat identical structures at multiple size scales. Each branch subdivides into smaller branches following the same geometric rules, creating self-similar patterns that mathematicians recognize as deterministic fractals. The branching maximizes surface area for nutrient absorption, while maintaining efficient transport networks for distributing resources throughout the organism. Modern corals and sponges use similar fractal architectures, demonstrating that these mathematical principles represent optimal solutions to biological engineering problems. The feeding strategies employed by Ediacaran organisms suggest they harvest nutrients through passive absorption rather than active predation. Most fossils lack evidence of mouths, guts, or other structures associated with animal feeding, instead showing highly folded surfaces that maximize contact with surrounding seawater. The organisms probably absorb dissolved organic compounds and bacteria directly through their cell membranes, a strategy that works efficiently in the nutrient-rich waters that characterize post-snowball ocean conditions. This osmotrophic lifestyle requires precise regulation of internal chemistry to maintain concentration gradients that drive nutrient uptake. Sexual reproduction appears for the first time during the Ediacaran period, introducing genetic recombination as a mechanism for generating biological diversity. The process requires coordination between different individuals to produce gametes, transfer genetic material, and develop fertilized embryos into functional adults. Sexual reproduction involves substantial energetic costs compared to asexual division, yet provides crucial advantages for populations facing environmental uncertainty. The genetic shuffling creates variation that allows rapid adaptation to changing conditions, while removing harmful mutations that accumulate in asexually reproducing lineages. Cell differentiation reaches new levels of sophistication as Ediacaran organisms develop specialized tissues for specific functions. Photosynthetic cells concentrate in surface layers to maximize light capture, while structural cells in interior regions provide mechanical support. Transport cells form networks that distribute nutrients and waste products throughout the organism, creating primitive circulatory systems that operate through diffusion rather than active pumping. The cellular division of labor increases efficiency while allowing organisms to grow larger than the size limits imposed by simple diffusion processes. The fossil preservation of Ediacaran organisms occurs under exceptional circumstances that capture soft tissue details normally lost during decomposition. Fine-grained sediments settle rapidly over the organisms, creating anaerobic conditions that prevent bacterial decay, while pressure from overlying sediments compresses the tissues into thin films. Pyritization replacement of organic matter by iron sulfide minerals preserves cellular structures and even subcellular organelles in some specimens. These preservation processes operate according to chemical principles that require precise timing and environmental conditions rarely achieved in normal marine settings. Mobility develops gradually during the Ediacaran period, as some organisms evolve the ability to crawl along the seafloor in search of favorable feeding locations. Trace fossils preserve evidence of simple locomotion patterns, straight trails, curved paths, and spiral tracks that suggest organisms could sense and respond to environmental gradients. The movement mechanisms probably involve changes in body shape through hydraulic pressure rather than the muscular contractions that characterize later animals. These primitive locomotion systems demonstrate how biological engineering can achieve complex behaviors through relatively simple mechanical principles. The Ediacaran period witnesses the first appearance of predation as some organisms develop the ability to consume other organisms rather than simply absorbing dissolved nutrients. Bite marks and borings in fossil shells provide evidence that predator-prey relationships had evolved by the end of the period, introducing ecological dynamics that would drive much of subsequent evolutionary change. The arms race between predators and prey accelerates the evolution of defensive structures like shells and spines, while favoring more efficient locomotion and sensory systems in both hunters and hunted. Biomineralization. The biological precipitation of mineral skeletons begins during the late Ediacaran, as organisms start depositing calcium carbonate, calcium phosphate, and silica structures for protection and support. The process requires precise control of local chemistry to supersaturate fluids with respect to specific minerals, while preventing precipitation in unwanted locations. Organic matrices guide crystal nucleation and growth, creating composite materials that combine the strength of minerals with the flexibility of organic polymers. These biological materials often exceed the mechanical properties of purely inorganic structures through their sophisticated hierarchical architectures. The geographic distribution of Ediacaran fossils suggests that these organisms achieved global dispersal despite their limited mobility. Similar species appear on different continents that were separated by thousands of kilometers of ocean, indicating that larvae or reproductive stages could survive long-distance transport by ocean currents. This cosmopolitan distribution demonstrates that biological complexity had reached levels sufficient to overcome geographical barriers and establish worldwide ecosystems. The global nature of Ediacaran biotas foreshadows the planetary-scale evolutionary radiations that will characterize subsequent periods. Atmospheric oxygen concentrations during the Ediacaran period approach levels sufficient to support animal metabolism for the first time in Earth's history. The oxygen increase results from enhanced organic carbon burial during and after the snowball glaciations, which removes carbon from the atmosphere-ocean system and allows oxygen to accumulate. Higher oxygen levels support the aerobic respiration needed to power active lifestyles and maintain the complex biochemistry required for multicellular development. The oxygen rise represents an essential prerequisite for the evolution of large, metabolically active organisms. The mystery that fascinates paleontologists is how Ediacaran organisms achieved such sophisticated body plans without the developmental genes that control embryonic patterning in modern animals. Molecular phylogenetic studies suggest that many key regulatory genes evolved after the Ediacaran period, implying that these early organisms used different mechanisms to coordinate multicellular development. Whether these alternative systems represent evolutionary dead ends or precursors to modern developmental biology remains one of the most intriguing questions in evolutionary science. The transition from Ediacaran to Cambrian faunas involves the apparent disappearance of most Ediacaran body plans and their replacement by organisms with fundamentally different architectures. Whether this represents mass extinction, followed by evolutionary replacement or gradual transformation of existing lineages, continues to generate scientific debate. The boundary between these periods marks one of the most dramatic transitions in the history of life, setting the stage for the explosive diversification that will characterize the Cambrian period. Only took 20 million years to invent multicellular construction techniques that would serve as the foundation for all subsequent biological complexity. Yet the Ediacaran engineering projects achieved levels of sophistication that rival modern architectural designs. These ancient organisms established the basic principles of biological assembly, modular construction, fractal organization, cellular specialization, and developmental coordination that continue to operate in every complex organism alive today. Following the same geometric and thermodynamic rules that governed Earth's first experiments with multicellular life, 540 million years ago, life unleashes its most spectacular burst of creativity in what paleontologists call the Cambrian explosion. A 25 million year period of evolutionary innovation that produces virtually every major animal body plan that exists today. The diversification occurs with the precision of a vast manufacturing operation, each new species emerging with complex anatomical features that appear fully functional from their first appearance in the fossil record. Yet, beneath this apparent spontaneity lies adherence to fundamental engineering principles and developmental constraints that guide the construction of biological complexity according to physical laws discovered billions of years before consciousness evolved to comprehend them. The trilobites exemplify the sophisticated engineering that characterizes Cambrian life. These arthropods develop compound eyes, containing thousands of individual lenses, each one a precisely shaped calcite crystal that focuses light according to optical principles governing refraction and lens geometry. The lenses follow mathematical curves called aplanatic surfaces that minimize spherical aberration and produce sharp images across wide fields of view. Some trilobite eyes achieve optical performance that approaches the theoretical limits imposed by the wave nature of light, creating visual systems that marine engineers study for inspiration in designing underwater cameras and periscopes. Anomalocaris, the apex predator of Cambrian seas, demonstrates how biological systems scale mechanical structures to achieve large size while maintaining functionality, growing to lengths exceeding 2 meters. This arthropod develops flexible grasping appendages that operate through hydraulic pressure changes rather than rigid joints. The appendages contain internal chambers that can be inflated or deflated to create controlled movements with multiple degrees of freedom, similar to elephant trunks or octopus arms. The hydraulic actuators provide strength and precision while remaining lightweight enough for rapid swimming, illustrating how biological engineering solves scaling problems through innovative mechanical designs. Hallucigenia and other bizarre Cambrian creatures exhibit defensive strategies based on mathematical principles governing structural optimization. The organism's dorsal spines follow spacing patterns that maximize coverage while minimizing material costs, creating protective arrays that deflect predator attacks with maximum efficiency. The spine geometry follows engineering principles used in modern composite materials, where fiber reinforcement provides strength in specific directions while remaining flexible under different loading conditions. Each spine acts as a cantilever beam designed to absorb impact energy without breaking, demonstrating sophisticated understanding of structural mechanics at the cellular level. The Burgess Shale preserves soft tissue details through fossilization processes that operate like biological xerography machines, capturing anatomical structures down to subcellular levels of detail. Rapid burial in fine sediments creates anaerobic conditions that prevent decomposition, while pressure from overlying layers compresses organisms into thin films. Replacement of organic carbon by clay minerals preserves even delicate structures like gills, muscles, and digestive systems that normally decay within hours of death. The preservation process requires precise coordination of sedimentation rates, oxygen levels, and chemical conditions that occur rarely in normal marine environments. Brachiopods engineer shells using crystallographic principles that maximize strength while minimizing weight. The shell structure consists of calcite crystals oriented with their C-axes perpendicular to the shell surface, creating composite materials with strength properties that vary directionally according to loading requirements. Internal reinforcing ribs follow geometric patterns based on minimal surface mathematics, distributing stress efficiently while using minimum amounts of calcium carbonate. The shell architecture achieves strength-to-weight ratios that exceed those of many modern engineering materials through sophisticated hierarchical organization spanning multiple length scales. Mollusks develop coiling patterns in their shells that follow logarithmic spirals with mathematical precision. The spiral geometry maintains constant proportions as the organism grows, allowing continuous expansion without requiring complete reconstruction of existing shell material. The coiling follows rules discovered much later by mathematicians studying growth patterns in biological systems. Each new chamber maintains the same shape as previous chambers while increasing in size by a constant factor. This geometric constraint creates the beautiful spiral forms visible in nautiloids, gastropods, and other shelled mollusks throughout the geological record. Echinoderms construct skeletons using crystalline architectures that seem almost impossible from an engineering perspective. Each skeletal plate consists of a single calcite crystal despite containing complex three-dimensional networks of pores and channels. The crystal lattice remains perfectly aligned throughout the entire structure, creating materials that combine the optical properties of single crystals with the mechanical properties of complex composites. Modern materials scientists study echinoderm skeletons to understand how biological systems achieve structural sophistication that exceeds current manufacturing capabilities. The development of mineralized skeletons during the Cambrian follows thermodynamic principles governing crystal nucleation and growth in biological systems. Organisms must supersaturate their body fluids with respect to specific minerals while controlling where and when precipitation occurs. Organic matrices provide nucleation sites and guide crystal orientation, creating composite materials that combine mineral strength with organic flexibility. The biomineralization process requires precise regulation of pH, ionic concentrations, and protein expression patterns that coordinate chemical and biological processes at molecular scales. Arthropod exoskeletons demonstrate solutions to the fundamental engineering problem of creating flexible joints in rigid materials. The cuticle consists of layers of chitin fibers embedded in protein matrices, with fiber orientations varying between layers to create materials with complex mechanical properties. Joint regions have reduced mineral content and specialized fiber architectures that permit controlled deformation while maintaining structural integrity under loading. The exoskeleton design allows rapid locomotion while providing protection from predators, illustrating how biological engineering balances competing functional requirements. Filter feeding strategies developed by many Cambrian organisms follow fluid dynamic principles governing particle capture in flow systems. Crinoids and other suspension feeders position their feeding appendages to create optimal flow patterns that maximize encounter rates with food particles while minimizing energy expenditure. The feeding structures follow mathematical relationships between flow velocity, particle size, and capture efficiency that determine optimal spacing and orientation of filtering elements. These biological designs achieve particle separation efficiencies that rival those of modern industrial filtration systems. The Cambrian explosion coincides with atmospheric oxygen concentrations reaching levels sufficient to support active metabolism in large organisms. Oxygen availability determines the maximum size that organisms can achieve through simple diffusion processes, while higher concentrations enable the evolution of circulatory systems that transport oxygen to internal tissues. The oxygen threshold for complex life appears to be remarkably precise. Too little prevents sufficient energy production for active behavior, while too much creates oxidative stress that damages cellular components. Cambrian oxygen levels fall within the narrow range that optimizes both energy production and cellular protection. Predator-prey arms races accelerate evolutionary innovation as organisms develop increasingly sophisticated offensive and defensive capabilities. The appearance of predators with grasping appendages, crushing claws, and boring capabilities drives the evolution of shells, spines, and escape behaviors in prey species. Each improvement in predatory efficiency selects for better defensive measures, while enhanced prey defenses favor more effective predatory strategies. This evolutionary feedback operates according to game-theoretic principles that favor strategies providing maximum advantage over competing approaches. The geographic distribution of Cambrian faunas reflects ocean circulation patterns and continental configurations that create distinct biogeographic provinces with characteristic assemblages of organisms. Different regions develop unique evolutionary lineages that reflect local environmental conditions and historical contingencies affecting colonization and extinction events. The biogeographic patterns provide evidence that biological diversity results from complex interactions between evolutionary processes and physical environmental factors operating at global scales. Developmental genetics begins operating through regulatory gene networks that control embryonic patterning with digital precision. Homeotic genes specify body segment identity through combinatorial expression patterns that create positional information along anterior, posterior, and dorsal ventral axes. The genetic regulatory circuits follow Boolean logic relationships that process input signals and generate appropriate developmental responses. These molecular control systems achieve the coordination between different cell types and tissues required for complex multicellular organization. The mystery that puzzles evolutionary biologists is how such dramatic morphological innovation occurred within such a geologically brief time period. The Cambrian explosion produces more new body plans in 25 million years than have appeared in the subsequent 500 million years of animal evolution. Whether this represents rapid evolutionary change driven by ecological opportunity or simply improved preservation conditions that make existing diversity visible in the fossil record remains one of paleontology's most contentious debates. The end of the Cambrian period sees the establishment of modern marine ecosystem structures with complex food webs including primary producers, herbivores, carnivores, and decomposers. The ecological relationships follow energy flow principles that govern all subsequent biological communities, with approximately 10% energy transfer efficiency between trophic levels and biomass pyramids that reflect thermodynamic constraints on ecosystem productivity. These fundamental ecological patterns persist throughout the remainder of Earth's history. Only took 25 million years to establish the basic body plans that would dominate animal life for the next 500 million years. Yet the Cambrian manufacturing burst achieved levels of biological innovation that required adherence to precise engineering principles and developmental constraints. The explosion demonstrates how evolutionary processes can rapidly explore morphological possibilities while remaining constrained by physical laws that govern structural mechanics, fluid dynamics, and material science, creating the biological architectures that continue to operate according to the same fundamental principles today. 450 million years ago, Earth begins a series of mass extinction renovations that systematically clear biological real estate and rebuild ecosystems according to new architectural specifications. The Ordovician-Silurian extinction removes 85% of marine species in what appears to be catastrophic destruction. Yet the elimination follows precise patterns that suggest quality control procedures rather than random annihilation. Each of the 5 major extinction events operates according to selectivity rules that preferentially eliminate certain types of organisms while preserving others, creating ecological vacancies that drive subsequent adaptive radiations following mathematical principles governing competitive exclusion and niche partitioning. The late Ordovician extinction begins when atmospheric carbon dioxide concentrations drop rapidly due to enhanced silicate weathering as the supercontinent Gondwana drifts over the South Pole. Tropical reef systems that had flourished in warm, high carbon dioxide seas suddenly face cooling temperatures and reduced atmospheric greenhouse warming. The extinction proceeds in 2 distinct pulses separated by several 100,000 years, each one eliminating different ecological groups according to their physiological tolerances and habitat requirements. Cold water specialist organisms survive while warm water tropical species disappear, demonstrating how climate change operates as a selective filter that sorts biological diversity according to environmental preferences. The late Devonian extinction unfolds over several million years as ocean chemistry changes eliminate the marine ecosystems that had dominated Middle Paleozoic seas. Massive coral and stromatoporoid reefs that covered extensive areas of shallow tropical seas disappear permanently. never to be rebuilt on similar scales. The extinction mechanism involves oceanic anoxia depletion of dissolved oxygen that makes marine environments uninhabitable for most complex organisms. The anoxic conditions spread through ocean basins according to circulation patterns and density stratification, creating dead zones that expand systematically from deep waters toward the surface. The Permian-Triassic extinction represents the most thorough biological renovation in Earth's history, eliminating 96% of marine species and 70% of terrestrial vertebrates in what paleontologists call the Great Dying. The extinction mechanism involves massive volcanic eruptions in Siberia that release millions of cubic kilometers of lava and unprecedented volumes of greenhouse gases into the atmosphere. The Siberian Traps volcanism operates for approximately 1 million years, injecting carbon dioxide, sulfur dioxide, and other gases into the atmosphere at rates that overwhelm natural buffering systems and trigger runaway climate change. The volcanic emissions acidify the oceans through carbonic acid formation when atmospheric carbon dioxide dissolves in seawater. Ocean pH drops by approximately 0.7 units, a change large enough to dissolve calcium carbonate shells and skeletons of marine organisms. The acidification preferentially affects organisms that build mineralized structures, eliminating most brachiopods, corals, and other shelled marine animals while allowing soft-bodied organisms to survive the chemical crisis. The selectivity pattern suggests that extinction mechanisms operate according to biochemical vulnerabilities rather than random sampling of biological diversity. The Triassic-Jurassic extinction coincides with the breakup of the supercontinent Pangaea and massive volcanism associated with the opening of the Atlantic Ocean. The Central Atlantic Magmatic Province produces flood basalts covering millions of square kilometers while releasing greenhouse gases that cause rapid global warming. The extinction eliminates many archaic reptile groups and creates ecological opportunities for dinosaurs to diversify and dominate terrestrial ecosystems for the following 150 million years. The timing demonstrates how geological processes and biological evolution operate through coupled feedback mechanisms. The Cretaceous-Paleogene extinction operates through impact winter conditions following the collision of a 10-kilometer asteroid with Earth's surface at the Yucatan Peninsula. The impact releases energy equivalent to several billion nuclear weapons and ejects massive quantities of rock vapor and debris into the atmosphere. The debris cloud blocks sunlight for months or years, causing global cooling and collapse of photosynthetic productivity. The extinction preferentially eliminates large-bodied organisms that require high metabolic rates while allowing smaller creatures to survive on limited food resources. Each extinction event creates ecological vacancies that drive subsequent adaptive radiations following predictable patterns based on competitive exclusion principles and resource partitioning theory. Empty ecological niches provide opportunities for surviving lineages to diversify and exploit previously unavailable resources. The adaptive radiations occur rapidly in geological terms, often producing new body plans and ecological strategies within a few million years of the extinction event. The recovery dynamics follow mathematical relationships governing population growth, species interactions, and evolutionary optimization. The selectivity patterns observed across multiple extinction events reveal consistent biases in survival and extinction probabilities based on organism characteristics. Large-bodied species face higher extinction risks than small-bodied ones due to their greater resource requirements and smaller population sizes. Geographically widespread species survive better than those with restricted ranges because local environmental perturbations cannot eliminate their entire populations. Organisms with broad ecological tolerances show greater survival rates than specialists adapted to specific environmental conditions. Marine organisms experience higher extinction rates than terrestrial ones, during most mass extinction events due to the different buffering capacities of oceanic and atmospheric systems. Ocean chemistry changes more slowly than atmospheric composition, but persists for longer periods once established, creating sustained stress conditions that eliminate marine species over extended time intervals. Terrestrial environments show greater spatial heterogeneity that provides refugia where organisms can survive regional environmental perturbations, allowing faster recovery following extinction events. Recovery from mass extinctions follows predictable stages, beginning with disaster taxa opportunistic species that rapidly colonize empty habitats but lack the specialized adaptations needed for long-term success. These pioneer species provide ecological services that facilitate the establishment of more specialized organisms during later recovery phases. The succession proceeds according to ecological principles governing community assembly, with diversity and complexity increasing systematically as ecosystems rebuild their functional networks and energy flow pathways. The fossil record preserves evidence that biological innovation accelerates following mass extinction events as surviving lineages diversify to fill empty ecological roles. Many major evolutionary innovations appear in the aftermath of extinctions, including the origins of modern reef ecosystems, complex flowering plant communities, and mammalian adaptive radiations. The pattern suggests that mass extinctions remove competitive constraints that normally prevent major evolutionary changes, allowing rapid exploration of new morphological and ecological possibilities. Geochemical signatures in sedimentary rocks reveal that mass extinctions often coincide with perturbations in global biogeochemical cycles, including carbon, sulfur, and nitrogen cycling. The cycle disruptions reflect the collapse of biological productivity and the reorganization of elemental reservoirs between atmosphere, ocean, and terrestrial systems. Recovery involves the re-establishment of stable biogeochemical cycling through the evolution of new biological communities capable of processing elements at rates sufficient to maintain global equilibrium. The spacing between major extinction events appears non-random, with intervals of approximately 26 million years between some events suggesting possible astronomical forcing mechanisms. Proposed causes include periodic comet showers associated with the solar system's oscillation through the galactic plane or perturbations of the Oort cloud by nearby stars. However, the evidence for periodic extinction remains controversial, and most events can be explained by terrestrial processes including volcanism, climate change, and oceanic reorganization. The magnitude of species lost during mass extinctions follows power law relationships that suggest the extinction process operates according to self-organized criticality principles, similar to those governing earthquake distributions and forest fire patterns. The mathematical relationships imply that extinction events represent phase transitions in ecological systems rather than simple responses to external perturbations. Small environmental changes can trigger cascading failures that propagate through ecological networks and cause disproportionately large biodiversity losses. The mystery that intrigues paleontologists is how ecosystems manage to rebuild their complexity following such severe disruptions to biological diversity and ecological function. The recovery process requires coordinated evolution of multiple interacting species that must develop compatible ecological roles and maintain stable population dynamics. The speed and consistency of ecosystem recovery suggests that biological systems possess inherent self-organizing properties that guide community assembly according to optimization principles, operating at ecosystem scales. Modern extinction rates appear to exceed background levels by factors of 100 to 1,000, suggesting that human activities may be triggering the sixth major mass extinction event in Earth's history. The current extinction shows selectivity patterns similar to previous events, with large-bodied species, narrow-range endemics, and ecological specialists facing the highest risks. Whether ecosystems will recover from anthropogenic extinctions following the same patterns observed for previous events remains one of the most pressing questions in conservation biology. Only took 5 major renovation projects spanning 400 million years to reshape life on Earth through systematic elimination and reconstruction cycles. Yet each extinction recovery sequence followed precise selectivity rules and recovery dynamics that maintained the fundamental properties of biological complexity while allowing exploration of new evolutionary possibilities. The mass extinctions demonstrate how destructive processes can serve constructive functions in biological systems, creating opportunities for innovation while maintaining the essential ecological relationships that sustain planetary habitability. 250 million years ago, the supercontinent Pangaea begins its slow-motion disassembly, setting in motion a continental drift mechanism that will redistribute land masses and reorganize global climate patterns with the precision of a planetary gear system. The breakup follows predictable sequences governed by lithospheric stress patterns and mantle convection dynamics, yet produces geographic configurations that seem almost intentionally designed to maximize biological diversity and climate stability. Each stage of continental separation creates new ocean basins, alters atmospheric and oceanic circulation, and provides fresh evolutionary opportunities that drive adaptive radiations across isolated land masses. The initial rifting begins along zones of crustal weakness where ancient suture zones mark the collision boundaries that assembled Pangaea during the late Paleozoic. Tensional stresses concentrate along these pre-existing fractures, creating rift valleys that gradually widen as mantle upwelling generates new oceanic crust. The process follows mechanical principles governing rock failure. Under tension, stress concentrates at crack tips until the local strength is exceeded, allowing fractures to propagate according to the direction of maximum principal stress. The continental breakup operates like a controlled demolition that follows structural weak points to achieve systematic disassembly. The Central Atlantic opens first as North America separates from Africa, beginning approximately 200 million years ago. The spreading process creates the Mid-Atlantic Ridge, where basaltic magma wells up from the mantle to form new oceanic crust at rates of 2 to 4 centimeters per year. The spreading follows the same mechanisms that operate at modern oceanic ridges. Partial melting of ascending mantle material produces magmas that crystallize to form the oceanic lithosphere. Magnetic stripes in the oceanic crust preserve a record of ancient magnetic reversals, providing compelling evidence that seafloor spreading has operated continuously since continental breakup began. The separation of South America from Africa occurs along a nearly straight line that creates the South Atlantic Ocean with remarkable geometric precision. The continental margins fit together like puzzle pieces with corresponding geological formations, fossil assemblages, and structural trends continuing across the ocean basin. The match demonstrates that continental drift has moved the land masses thousands of kilometers from their original positions while preserving the detailed correspondence of features that were once continuous. The geometric fit provides conclusive evidence that the continents were formerly joined in a single supercontinent. India begins its northward journey from Antarctica approximately 160 million years ago, traveling across the ancient Tethys Ocean at speeds reaching up to 20 centimeters per year, exceptionally fast for plate tectonic motions. The Indian subcontinent operates like a massive oceanic liner crossing half the planet before colliding with Asia 50 million years ago. The collision creates the Himalayan mountain range and the Tibetan plateau through compressive deformation that continues today. The India-Asia collision demonstrates how continental drift can reshape entire regions and create topographic features that affect global climate patterns. The opening of the Atlantic Ocean fundamentally alters global oceanic circulation by creating new pathways for water mass exchange between ocean basins. The circulation changes affect heat transport from equatorial to polar regions, influencing global temperature patterns and ice sheet stability. Computer models of ancient ocean circulation show that continental configurations exert primary control over oceanic heat transport, with small changes in gateway geometry producing large effects on regional climate. The continental positions seem precisely arranged to maintain global climate stability while preventing extreme icehouse or greenhouse conditions. The breakup of Pangaea isolates biological populations on different continents, creating independent evolutionary experiments that produce distinct biogeographic patterns. Gondwanan landmasses share similar fossil assemblages that reflect their common ancestry, while Laurasian continents develop different evolutionary trajectories following their separation from southern landmasses. The biogeographic patterns provide powerful evidence for continental drift while demonstrating how geographic isolation drives speciation and adaptive radiation. Each continent becomes a separate laboratory for evolutionary innovation. The formation of new ocean basins creates marine seaways that connect previously isolated water masses and allow biological exchange between different oceanic provinces. The Tethys Seaway, which separates northern and southern land masses for much of the Mesozoic, facilitates east-west biological dispersal and creates the warm, equatorial circulation patterns that characterize greenhouse climate conditions. The seaway configurations affect global ocean chemistry by controlling the mixing rates between different water masses with distinct temperature, salinity, and nutrient characteristics. Volcanic activity associated with continental rifting releases massive quantities of carbon dioxide and other greenhouse gases that influence global climate throughout the breakup process. The Central Atlantic Magmatic Province erupts approximately 200 million years ago, coinciding with the Triassic-Jurassic extinction and the onset of Jurassic warming. The Deccan Traps volcanism occurs during the final stages of India's northward drift, contributing to the environmental changes that characterize the Cretaceous-Paleogene boundary. The timing relationships suggest that continental drift and climate change operate through coupled feedback mechanisms. The elevation of continental surfaces changes systematically during continental drift as thermal subsidence affects the buoyancy of continental lithosphere. Recently rifted continental margins sit at high elevations due to thermal expansion and reduced lithospheric density associated with heating during breakup. As the continents drift away from spreading centers, they cool and subside, creating the characteristic pattern of coastal plains and continental shelves that characterize passive margins. The subsidence follows exponential decay curves that reflect the thermal properties of lithospheric rocks. Sea level variations throughout the continental drift process result from changes in oceanic ridge volume and continental elevation that affect the capacity of ocean basins. High spreading rates during the early stages of breakup create voluminous oceanic ridges that displace seawater and cause global sea level rise. As spreading rates decrease and oceanic lithosphere cools, the ridges subside and ocean basin capacity increases, causing sea level fall. The sea level changes affect continental flooding and the distribution of marine and terrestrial environments across the globe. The assembly of new mountain ranges through continental collision creates topographic barriers that affect atmospheric circulation patterns and regional climate. The rise of the Himalayas and Tibetan Plateau fundamentally alters the Asian monsoon system by creating orographic effects that enhance precipitation patterns and seasonal temperature variations. The mountain building also accelerates silicate weathering rates by exposing fresh rock surfaces to chemical attack, removing carbon dioxide from the atmosphere and contributing to global cooling trends. The Wilson cycle describes the complete sequence of ocean basin opening, maturation, and closure that characterizes the long-term behavior of continental drift. Ocean basins begin as continental rifts, develop into narrow seas like the Red Sea, mature into broad oceans like the Atlantic, then begin closing through subduction until continents collide and the ocean disappears entirely. The cycle requires approximately 400 to 500 million years to complete and has operated repeatedly throughout Earth's history, creating a predictable rhythm of supercontinent assembly and dispersal. The fragmentation of Pangaea creates the modern biogeographic pattern of continental endemism, where different land masses support distinct assemblages of organisms that reflect their evolutionary history and geographic isolation. Australia's unique marsupial fauna, Madagascar's endemic lemurs, and South America's distinctive mammalian groups all result from continental drift that isolated ancestral populations and allowed independent evolutionary development. The biogeographic patterns provide natural experiments that reveal how geographic separation affects evolutionary processes. Hotspot volcanism creates chains of volcanic islands that track the motion of oceanic plates over stationary mantle plumes. The Hawaiian Emperor Seamount chain preserves a record of Pacific plate motion over the past 70 million years, showing changes in both velocity and direction that reflect alterations in plate boundary forces. The hotspot tracks provide independent evidence for plate motions while demonstrating how deep mantle processes interact with surface tectonics to create volcanic features. The mystery that fascinates geologists is how continental drift maintains the delicate balance between climate stability and biological diversity over geological timescales. Too much continental fragmentation creates excessive geographic isolation that reduces biological exchange and evolutionary innovation. Too little fragmentation produces climate instability and reduced environmental diversity that limits speciation opportunities. Earth's continental drift patterns seem precisely calibrated to optimize both climate regulation and biological diversification throughout the planet's history. Paleomagnetic studies reveal that continental drift has operated continuously for at least the past 3 billion years, yet the process maintains remarkable consistency in spreading rates, ridge geometries, and subduction dynamics. The long-term stability of plate tectonic processes suggests that continental drift represents a fundamental property of planetary thermal evolution rather than a transient phenomenon. The predictable nature of continental motions provides evidence that Earth's geological systems operate according to physical principles that maintain optimal conditions for surface habitability. Only took 250 million years to completely rearrange the global geography while maintaining the precise oceanic and atmospheric circulation patterns needed for climate stability. Yet continental drift continues operating with the same mechanical precision that has characterized plate tectonics throughout Earth's history. The ongoing motion of continents follows the same physical laws that governed Pangaea's breakup, demonstrating how geological processes maintain planetary habitability through continuous adjustment of surface configurations that optimize heat transport, ocean chemistry, and biological diversity. 2.5 million years ago, Earth's climate system enters an era of systematic oscillation as ice sheets advance and retreat across northern continents with the precision of a vast climatological metronome. The Quaternary ice ages operate according to astronomical forcing mechanisms that modulate solar radiation patterns on timescales of 20,000 to 100,000 years. Yet the climate response exhibits sophisticated amplification and feedback processes that transform subtle orbital variations into dramatic environmental changes. These glacial-interglacial cycles serve as a global climate control system that maintains long-term temperature stability while driving evolutionary adaptation and landscape modification through systematic environmental variation. The Milankovitch cycles provide the fundamental timing mechanism for ice age oscillations through three distinct orbital parameters that vary on different timescales. Earth's axial tilt oscillates between 22 and 24 degrees over 41,000-year cycles, controlling the contrast between summer and winter temperatures at high latitudes. The orbital eccentricity varies on approximately 100,000-year cycles, modulating the difference between closest and farthest approach to the Sun during each year. The precession of equinoxes operates on 21,000-year cycles, determining which hemisphere receives peak solar heating during different seasons. The orbital variations create only modest changes in total solar radiation received by Earth. Yet these small perturbations trigger massive climate responses through positive feedback mechanisms that amplify the initial forcing. Ice albedo feedback operates as the primary amplification system when summer temperatures cool enough to prevent complete melting of winter snow accumulation. Ice sheets begin growing and reflecting increasing amounts of solar radiation back to space. The enhanced reflection causes additional cooling that allows further ice sheet expansion, creating a runaway process that can transform regional cooling into continental glaciation. The Laurentide ice sheet demonstrates how astronomical forcing translates into geological scale landscape modification through systematic ice accumulation and flow. Beginning as isolated ice caps in the Canadian Arctic, the ice sheet grows during glacial periods to cover most of northern North America with ice thicknesses exceeding 3 kilometers. The ice flows according to gravitational potential gradients, carving valleys, transporting sediments, and reshaping topography through erosional processes that operate with the efficiency of continental-scale bulldozers. The ice sheet behavior follows fluid dynamics, principles scaled up to continental dimensions. Oceanic circulation patterns reorganize systematically during glacial-interglacial transitions as changing ice sheet configurations alter atmospheric pressure patterns and wind systems. The Atlantic meridional overturning circulation, the oceanic conveyor belt that transports warm surface water northward and cold deep water southward, strengthens and weakens according to freshwater inputs from melting ice sheets and changes in surface water density. The circulation changes affect heat transport between low and high latitudes, creating regional climate variations that can occur within decades despite the millennial timescales of orbital forcing. Sea level variations during ice age cycles follow simple mass conservation principles as water transfers between oceanic and ice sheet reservoirs. During peak glacial periods, sea level drops by approximately 120 meters as continental ice sheets sequester water equivalent to roughly 3% of the total oceanic volume. The sea level changes expose vast areas of continental shelf that become available for terrestrial colonization, creating land bridges between previously isolated continents and islands. The exposed shelves provide migration corridors that facilitate biological dispersal and evolutionary exchange between different biogeographic regions. Atmospheric carbon dioxide concentrations oscillate between approximately 180 and 300 parts per million during glacial-interglacial cycles, providing additional climate forcing that amplifies the orbital signals. The carbon dioxide variations result from changes in oceanic circulation, marine biological productivity, and terrestrial carbon storage that affect the partitioning of carbon between atmospheric, oceanic, and biospheric reservoirs. Ice core records preserve detailed histories of atmospheric composition that reveal how biogeochemical cycles respond to climate forcing on millennial timescales. The timing relationships between orbital forcing and climate response demonstrate sophisticated phase relationships that reflect the complex dynamics of ice sheet growth and decay. Ice sheets respond slowly to orbital forcing due to their large thermal inertia and the time required for ice accumulation and flow. The delayed response creates phase lags between maximum orbital forcing and peak glacial conditions, with ice sheets reaching maximum extent several thousand years after the astronomical conditions that initiated their growth. The phase relationships provide insights into the mechanical properties and response times of continental ice sheets. Vegetation patterns shift systematically across continents as climate zones migrate with changing ice sheet configurations and atmospheric circulation patterns. Boreal forests advance and retreat over distances of thousands of kilometers, while tropical and temperate biomes expand and contract according to temperature and precipitation changes. The vegetation migrations occur rapidly enough to track climate changes, yet slowly enough to create refugia where species can survive unfavorable periods. The biological responses demonstrate how terrestrial ecosystems adapt to systematic climate variability. Loess deposits windblown sediments derived from glacial outwash plains preserve detailed records of atmospheric circulation patterns during glacial periods. The fine-grained sediments accumulate in thick sequences that record variations in wind strength, direction, and dust sources throughout multiple glacial-interglacial cycles. The Loess records reveal how continental-scale atmospheric circulation reorganizes in response to changing ice sheet topography and thermal gradients. The deposits provide terrestrial complements to marine sediment records that document oceanic changes. Lake-level variations in closed basins provide sensitive indicators of regional precipitation and evaporation balance during different climate states. Pluvial lakes in currently arid regions reach maximum extents during glacial periods when cooler temperatures and altered storm tracks increase effective moisture availability. The lake-level records reveal how regional water balance responds to global climate forcing, providing insights into the spatial patterns of climate change that affect biological habitats and human environments. Permafrost distribution expands and contracts with ice age cycles as ground temperatures fluctuate above and below freezing thresholds. During glacial periods, permafrost extends across vast areas of northern continents and high mountain regions, affecting hydrology, vegetation, and soil development. The permafrost changes alter landscape stability and carbon cycling as frozen organic matter becomes available for decomposition during warming periods. The permafrost dynamics provide feedback mechanisms that affect atmospheric greenhouse gas concentrations. The last glacial maximum, approximately 20,000 years ago, represents the most recent peak of continental glaciation when ice sheets reached their maximum extent and global climate conditions differed most dramatically from present-day patterns. Paleoclimate reconstructions reveal global temperature depressions of 4 to 7 degrees Celsius, altered precipitation patterns, and enhanced atmospheric dust loading that created Earth system conditions unlike any experienced during human civilization. The LGM provides a natural experiment that tests climate model predictions and reveals the range of climate variability possible within Earth's current orbital configuration. Abrupt climate changes during glacial periods demonstrate that Earth's climate system can reorganize rapidly when critical thresholds are exceeded. Dansgaard-Oeschger events, millennial-scale warming and cooling cycles recorded in Greenland ice cores show temperature changes of up to 15 degrees Celsius occurring within decades. The rapid transitions suggest that climate systems can exist in multiple stable states with sudden switches between different configurations when forcing exceeds threshold values. The abrupt changes reveal nonlinear climate dynamics that operate through tipping point mechanisms. The Younger Dryas event provides a dramatic example of abrupt climate reversal during the last glaciation, when rapid warming was interrupted by a return to near-glacial conditions for approximately 1,200 years. The event appears to result from massive freshwater inputs to the North Atlantic that disrupted oceanic circulation and reduced heat transport to high northern latitudes. The Younger Dryas demonstrates how ice sheet melting can trigger climate feedbacks that temporarily reverse warming trends despite continued orbital forcing toward interglacial conditions. Human evolution and migration patterns show strong correlations with Ice Age climate variability, as changing environments create selection pressures that drive morphological and behavioral adaptation. The expansion of early humans out of Africa occurs during periods of reduced aridity that create migration corridors through currently desert regions. Ice Age climate cycles affect resource availability, habitat distribution, and population connectivity in ways that influence human demographic history and cultural development. The climate forcing provides environmental context for understanding human evolutionary history. The mystery that puzzles climate scientists is how relatively small orbital variations produce such large and systematic climate responses through the complex feedback mechanisms that characterize Earth's climate system. The amplification requires precise coordination between atmospheric, oceanic, and cryospheric processes that operate on different timescales, yet maintain phase relationships that enhance rather than cancel orbital forcing. The climate system exhibits sensitivity levels that seem calibrated to produce maximum response to astronomical forcing while maintaining long-term stability. The future behavior of Ice Age cycles remains uncertain as anthropogenic greenhouse gas emissions alter atmospheric composition beyond the range experienced during natural climate variability. Current atmospheric carbon dioxide concentrations exceed peak interglacial values by significant margins and continue rising at rates that far exceed natural variations. Whether human forcing will prevent future glaciations or simply delay their onset depends on the magnitude and duration of anthropogenic emissions relative to the natural timescales of orbital forcing. Only took 2.5 million years to establish the systematic climate oscillations that continue today. Yet the Ice Age control system operates with such precision that it maintains global temperature within narrow bounds while providing the environmental variability that drives evolutionary adaptation and landscape evolution. The quaternary climate cycles demonstrate how astronomical forcing can control planetary environments through sophisticated feedback mechanisms that amplify weak signals into strong responses, creating the systematic environmental variation that has characterized Earth's recent geological history. 2 million years ago, Earth enters its most recent phase of environmental fine-tuning as quaternary climate oscillations accelerate evolutionary innovations and establish the precise atmospheric conditions that will support technological civilization. The Pleistocene epoch witnesses an unprecedented burst of biological creativity as rapidly changing environments drive adaptive radiations, megafaunal evolution, and the emergence of human intelligence, all occurring within climate cycles that maintain global habitability while providing sufficient environmental pressure to accelerate evolutionary change. These final adjustments to planetary systems demonstrate how geological and biological processes coordinate to create conditions optimal for the development of consciousness and culture. Mammalian megafauna evolved to extraordinary sizes during Pleistocene glacial cycles as cooling temperatures and expanding grasslands favor large-bodied herbivores capable of efficient thermoregulation and long-distance migration. Mammoth populations develop specialized adaptations including dense fur coats, fat reserves, and curved tusks for clearing snow from vegetation. The largest mammoth species reach shoulder heights of 4 meters and weights exceeding 12 tons, representing body sizes that approach the theoretical limits for terrestrial mammals based on structural engineering constraints and metabolic scaling relationships. Cave bear populations demonstrate how Ice Age climate cycles drive rapid evolutionary change through geographic isolation and environmental specialization. During glacial periods, bear populations retreat to separate refuge areas where they evolve distinct morphological characteristics adapted to local conditions. Interglacial warming allows population expansion and genetic exchange that prevents excessive divergence while maintaining adaptive diversity. The alternating isolation and connection create evolutionary dynamics that maximize both local adaptation and species-wide genetic diversity through natural selection operating at multiple spatial and temporal scales. Saber-toothed cats develop specialized hunting strategies optimized for the megafaunal prey communities that characterize Pleistocene ecosystems. The elongated canine teeth function as precision instruments for severing major blood vessels and causing rapid death in large prey animals. Biomechanical analyses reveal that saber-tooth morphology represents optimal solutions to engineering problems involving stress concentration, penetration mechanics, and bite force generation. The predator-prey relationships follow mathematical principles governing optimal foraging theory and evolutionary arms races between attack and defense strategies. Plant communities respond to glacial-interglacial cycles through systematic migrations that track suitable climate zones across continental landscapes. Pollen records preserved in lake sediments document the northward advance of temperate forests during interglacial warming and their southward retreat during glacial cooling. The migration rates reach several kilometers per year for some tree species, requiring coordinated dispersal mechanisms and establishment strategies that operate faster than typical ecological timescales. The plant responses demonstrate remarkable organizational capacity for tracking environmental change through space and time. Ocean circulation patterns during the Pleistocene established the thermohaline circulation system that characterizes modern oceanic heat transport. The formation of North Atlantic deep water through cooling and sinking of surface waters in the Greenland and Norwegian seas creates the oceanic conveyor belt that transports tropical heat toward polar regions. The circulation system operates according to precise density relationships that depend on temperature and salinity gradients maintained by evaporation, precipitation, and ice formation patterns. Small changes in freshwater inputs can alter circulation strength and affect global climate within decades. Atmospheric greenhouse gas concentrations during Pleistocene interglacials reach levels that provide optimal climate conditions for biological productivity and diversity. Carbon dioxide concentrations of approximately 280 parts per million create sufficient greenhouse warming to maintain ice-free conditions in most continental regions while preventing the extreme heat that would stress temperate and boreal ecosystems. The greenhouse gas levels represent a precise balance between glacial and thermal extremes that maximizes habitable area and climatic stability. Soil development accelerates during Pleistocene interglacials as warmer temperatures and increased precipitation enhance chemical weathering and biological activity. The formation of deep, fertile soils provides the agricultural foundation that will support human civilization, while the systematic soil renewal through glacial stripping and interglacial rebuilding maintains long-term productivity. The soil formation follows predictable sequences based on parent material, climate, topography, and time that create diverse soil types optimized for different agricultural applications. Lake and wetland systems reach maximum development during interglacial periods when moderate temperatures and stable precipitation patterns create optimal conditions for freshwater ecosystem productivity. These aquatic systems serve as biodiversity reservoirs, climate buffers, and freshwater storage facilities that regulate regional hydrology. The lake systems also provide detailed paleoclimate records through sediment cores that preserve pollen, diatoms, and chemical indicators of past environmental conditions. The freshwater resources represent essential infrastructure for biological communities and human societies. Volcanic activity during the Pleistocene creates the island archipelagos and continental volcanic systems that provide natural laboratories for evolutionary experimentation. Isolated volcanic islands support adaptive radiations that produce endemic species adapted to specific microenvironments and ecological niches. The volcanic soils provide exceptional fertility that supports high biological productivity, while the topographic diversity creates multiple climate zones within limited geographic areas. The volcanic systems demonstrate how geological processes create optimal conditions for biological innovation and diversification. Coastal environments undergo systematic reorganization as sea level oscillations expose and flood continental shelf areas throughout glacial-interglacial cycles. During low sea level stands, rivers extend across exposed shelves and create extensive deltaic systems that support diverse terrestrial and freshwater communities. High sea level periods flood these areas to create shallow marine environments with high biological productivity. The alternating terrestrial and marine conditions create dynamic ecosystems that support both migration corridors and evolutionary isolation mechanisms. Climate stability. During the Holocene, the current interglacial period that began 11,700 years ago provides the environmental foundation for the development of agriculture and technological civilization. Temperature and precipitation patterns remain remarkably constant compared to the dramatic variations that characterize glacial periods, allowing human societies to develop complex agricultural systems and permanent settlements. The climate stability seems precisely calibrated to permit cultural evolution while maintaining the environmental challenges that drive technological innovation. Human evolution accelerates dramatically during the Pleistocene as climate variability creates selection pressures that favor intelligence, cooperation, and technological innovation. Brain size increases by factors of 3 over 2 million years, while tool use becomes increasingly sophisticated and culturally transmitted. The human lineage develops unique characteristics including upright locomotion, opposable thumbs, complex language, and abstract reasoning that enable unprecedented manipulation of environmental resources. The evolutionary trajectory appears optimized for developing technological capabilities. Agricultural origins during the early Holocene demonstrate how climate stabilization enables the transition from hunting and gathering to food production systems that support dense populations and complex societies. The development of agriculture occurs independently in multiple regions following similar sequences of plant and animal domestication. The agricultural transition requires precise coordination between human cultural evolution and biological adaptation of crop species through selective breeding. The timing suggests that climate stability represents a necessary prerequisite for agricultural development. Megafaunal extinctions at the end of the Pleistocene eliminate most large mammal species through combinations of climate change and human hunting pressure. The extinctions follow predictable patterns based on body size, geographic distribution, and ecological specialization that suggest systematic rather than random elimination processes. The loss of megafauna fundamentally alters ecosystem structure and function while creating ecological opportunities that facilitate human expansion and agricultural development. The extinctions represent the first major human impact on global ecosystems. Atmospheric composition during the Holocene reaches levels that optimize conditions for photosynthesis, plant growth, and agricultural productivity. Carbon dioxide concentrations of approximately 270 parts per million provide sufficient atmospheric carbon for plant metabolism while maintaining moderate greenhouse warming. Oxygen levels near 21% support efficient animal respiration while preventing the fire hazards that would occur at higher concentrations. The atmospheric composition seems precisely tuned for supporting complex terrestrial ecosystems. The mystery that fascinates scientists is how Pleistocene environmental changes manage to accelerate biological and cultural evolution while maintaining the climate stability needed for complex ecosystem development. The glacial-interglacial cycles provide environmental variability that drives adaptive change, yet avoid the extreme conditions that would eliminate biological complexity entirely. The balance between stability and change appears optimized for promoting evolutionary innovation while preserving the ecological relationships that support planetary habitability. Modern climate conditions represent the culmination of 2 million years of systematic environmental fine-tuning that has produced optimal conditions for biological diversity, ecosystem productivity, and human civilization. The current interglacial provides climate stability unmatched in the geological record while maintaining the atmospheric composition and oceanic circulation patterns that support global habitability. The quaternary fine-tuning demonstrates how Earth's environmental systems continue evolving toward configurations that maximize biological and cultural complexity. Only took 2 million years to complete the final environmental adjustments that created conditions optimal for consciousness and civilization. Yet the Pleistocene fine-tuning process followed the same physical and biological principles that have governed Earth's evolution throughout its history. The recent environmental changes demonstrate how geological timescales compress into rapid evolutionary innovation when conditions favor biological and cultural complexity, creating the planetary environment that supports technological species capable of understanding their own cosmic context. 10,000 years ago, as the great ice sheets complete their retreat and Earth settles into the stable climate patterns of the Holocene, humanity emerges as the first species in the planet's history capable of conscious planetary engineering. The transition occurs with remarkable precision. Atmospheric carbon dioxide concentrations stabilize at levels that optimize plant growth and agricultural productivity. Sea levels reach configurations that create extensive, fertile river deltas and coastal plains. And global temperature patterns establish the moderate, predictable conditions that enable technological civilization to develop. These environmental specifications seem almost intentionally calibrated to support a species capable of understanding and eventually managing the very planetary systems that created it. The agricultural revolution begins simultaneously across multiple continents, as climate stabilization creates the predictable growing seasons essential for crop domestication. Wild grasses in the Fertile Crescent, rice in Asia, maize in Mesoamerica, and potatoes in the Andes undergo genetic modifications through human selection that transform them into highly productive food sources capable of supporting dense populations. The domestication process follows evolutionary principles that concentrate desirable traits while eliminating characteristics that reduce agricultural utility. Each crop species represents a collaborative engineering project between human intelligence and plant genetics. Urban civilization emerges as agricultural surpluses enable population concentrations and occupational specialization that drive technological innovation at unprecedented rates. Cities develop according to optimal size distributions that balance the economic advantages of concentration against the logistical challenges of resource transport and waste management. The urban scaling laws follow mathematical relationships that govern energy consumption, innovation rates, and economic productivity across different city sizes. These power law relationships suggest that urban development operates according to optimization principles that maximize both individual welfare and collective capability. Metallurgy develops through systematic exploration of mineral processing techniques that unlock the potential of Earth's geological resources for technological applications. The sequence from copper to bronze to iron follows thermodynamic principles governing melting temperatures and chemical reduction reactions that require increasingly sophisticated control of combustion processes. Each metallurgical advance enables new tools, weapons, and construction techniques that expand human capabilities for environmental manipulation. The technological progression demonstrates how materials science drives cultural evolution through enhanced resource utilization. Written language appears independently in multiple civilizations as the complexity of social organization exceeds the capacity of oral tradition for information storage and transmission. The development of symbolic representation systems enables accurate preservation and communication of abstract concepts across space and time. Written records create cumulative cultural memory that allows each generation to build upon previous knowledge rather than rediscovering fundamental principles. The information storage revolution provides the foundation for accelerating technological progress through systematic knowledge accumulation. Mathematical and scientific discoveries reveal the fundamental principles governing natural phenomena and enable predictive understanding of physical systems. Ancient astronomers map planetary motions with precision sufficient for calendar systems and navigation, while early engineers apply mechanical principles to construct complex machines and architectural structures. The development of quantitative methods transforms human understanding from qualitative description to mathematical prediction, creating the intellectual tools needed for systematic technological development. Global trade networks emerge as transportation technologies enable resource exchange across continental and oceanic distances. The Silk Road, maritime trading routes, and continental transportation systems create economic integration that distributes specialized products and technological innovations throughout human populations. Trade relationships follow economic principles governing comparative advantage and cost optimization that maximize overall productivity through regional specialization. The commercial networks provide information exchange mechanisms that accelerate cultural and technological diffusion. The Industrial Revolution represents humanity's first systematic application of scientific principles to large-scale resource transformation and energy utilization. Steam engines convert heat energy into mechanical work according to thermodynamic principles that enable unprecedented power levels for manufacturing and transportation. The factory system applies division of labor and mechanical precision to achieve production rates impossible through traditional craft methods. Industrial technology demonstrates how scientific understanding translates into engineering capabilities that transform human relationship with natural resources. Fossil fuel utilization provides access to concentrated energy sources that accumulated over geological timescales, enabling human activities to operate at scales comparable to natural geological processes. Coal, petroleum, and natural gas represent stored solar energy from ancient photosynthesis that human technology can release rapidly for mechanical work and chemical synthesis. The energy sources provide power densities sufficient for global transportation systems, industrial manufacturing, and urban infrastructure that support billions of people at unprecedented living standards. The scientific revolution establishes experimental methodology and mathematical modeling as systematic approaches for understanding natural phenomena and developing technological applications. The scientific method provides reliable procedures for testing hypotheses, eliminating false theories, and accumulating accurate knowledge about physical reality. Scientific institutions create social mechanisms for coordinating research efforts and ensuring quality control through peer review and replication requirements. The knowledge production system enables accelerating discovery rates through collaborative investigation. Global communication networks developed as electromagnetic technologies enable instantaneous information transmission across planetary distances. Telegraph, radio, and eventually internet systems create real-time coordination capabilities that support global economic integration and cultural exchange. The communication infrastructure follows network theory principles that optimize connectivity while minimizing costs through hub-and-spoke architectures and packet switching protocols. Global communications represent the technological nervous system that enables planetary-scale coordination of human activities. Medical advances extend human lifespan and reduce mortality rates through systematic application of biological understanding to disease prevention and treatment. Vaccination, antibiotics, and surgical techniques demonstrate how scientific knowledge translates into intervention capabilities that overcome natural limitations on human survival and reproduction. Public health systems apply epidemiological principles to control infectious diseases and maintain population health at scales impossible through individual medical care alone. Medical technology illustrates how scientific understanding enhances human biological performance. Space exploration extends human presence beyond Earth's surface for the first time in the planet's history, providing direct observation of Earth as a complete planetary system and enabling investigation of other worlds for comparative planetology. Spacecraft follow orbital mechanics principles that utilize gravitational forces for energy-efficient transportation through the solar system. Space technology demonstrates human capability for engineering systems that operate in the most extreme environments while providing new perspectives on Earth's unique characteristics and cosmic context. Computer technology develops as systematic methods for information processing and calculation enable automation of complex logical operations. Digital systems follow Boolean algebra principles that represent information as binary codes manipulated through electronic circuits operating at molecular scales. Computing power increases exponentially through miniaturization techniques that approach atomic dimensions while processing speeds reach frequencies comparable to natural molecular vibrations. Information technology represents the first human-created systems that exhibit complexity levels approaching those of biological organisms. Environmental monitoring systems provide comprehensive measurement of planetary conditions, including atmospheric composition, ocean chemistry, biodiversity patterns, and climate dynamics. Global sensor networks collect data at spatial and temporal resolutions that reveal Earth system behavior with unprecedented detail and accuracy. The monitoring capabilities enable detection of human impacts on planetary systems and provide early warning systems for environmental changes that could affect human welfare. Environmental science demonstrates how technological capabilities enable conscious planetary management. Genetic engineering technologies provide direct manipulation capabilities for biological systems, including crop improvement, medical treatment, and ecosystem management. Molecular biology techniques enable precise modification of genetic codes that control organism characteristics and biological processes. The biotechnology applications demonstrate how scientific understanding translates into intervention capabilities that enhance both human welfare and environmental sustainability. Genetic technologies represent humanity's first direct control over evolutionary processes. The mystery that fascinates historians of science is how human technological development has proceeded through systematic discovery of natural principles that seem almost designed to be discoverable and applicable to engineering projects. Each scientific breakthrough reveals new possibilities for technological applications that enhance human capabilities while providing tools for addressing the challenges created by previous technological advances. The progression suggests that natural laws exhibit properties that favor the development of intelligence capable of understanding and applying those same laws. Climate change represents humanity's first unintentional global-scale environmental modification as fossil fuel emissions alter atmospheric composition and trigger planetary system responses. The climate effects demonstrate how human activities have reached magnitudes comparable to natural geological processes, while revealing the complex feedback mechanisms that govern Earth system behavior. Climate science provides the knowledge base needed for conscious planetary management, while climate change creates the necessity for systematic environmental stewardship. Artificial intelligence development begins as computer systems achieve information processing capabilities that approach and potentially exceed human cognitive performance in specific domains. Machine learning algorithms follow optimization principles that enable automated discovery of patterns in complex datasets and autonomous decision-making in uncertain environments. AI systems represent the first human-created technologies that exhibit characteristics traditionally associated with intelligence, including learning, reasoning, and problem-solving capabilities. Only took 10,000 years for humanity to develop from agricultural societies to technological civilization capable of conscious planetary engineering. Yet, the progression followed systematic principles governing innovation, knowledge accumulation, and technological application that created capabilities for understanding and managing the very planetary systems that made human evolution possible. The Anthropocene represents Earth's transition from unconscious to conscious planetary management as intelligence becomes a geological force capable of directing its own future evolution. Now, as consciousness settles into its cosmic context, Earth's ancient rhythms continue their patient work beneath the surface of human awareness. The same tectonic forces that assembled continents still shift imperceptibly through deep time, moving land masses along trajectories measured in millimeters per year, yet spanning millions of centuries. Volcanic systems maintain their slow circulation of molten rock through the planet's interior, following convection patterns established when the first oceans condensed from steam. The iron core spins in its liquid embrace, generating magnetic fields that spiral through space in invisible geometries older than multicellular life. Ocean currents trace their ancient pathways across thermal gradients that connect equatorial heat with polar cold, maintaining the atmospheric circulation that has moderated planetary climate through ice ages and warm periods, mass extinctions, and evolutionary radiations. Water molecules cycle between sea and sky according to phase transition principles discovered by physicists but operated by thermodynamics for billions of years before intelligence evolved to comprehend their elegant mathematics. The carbon cycle breathes through geological timescales, exhaling volcanic carbon dioxide and inhaling limestone precipitation in rhythms that regulate atmospheric composition with the consistency of a planetary heartbeat. Deep beneath the continents, groundwater moves through pore spaces and fractures in slow underground rivers that began flowing when dinosaurs walked the surface, carrying dissolved minerals and trace elements through aquifer systems that will outlast technological civilization by eons. Mountain ranges continue their imperceptible rise and erosion, adding millimeters of elevation each year while streams carve valleys grain by grain, following gravitational potential gradients toward the sea. Soils develop their thin layers of biological activity according to chemical weathering rates that transform solid rock into the foundation for terrestrial life. Electromagnetic radiation from the sun arrives each morning at precisely the same 8-minute delay that has characterized Earth's orbital relationship since the planet settled into its current distance. Solar panels and photosynthesis both harvest photons according to quantum mechanical principles that operate identically in silicon semiconductors and chlorophyll molecules, converting light into useful energy through processes that mirror each other across the boundary between biological and technological systems. Atmospheric molecules scatter blue wavelengths while transmitting longer frequencies, creating the blue sky and red sunset that have remained constant through all of human history. In the deep ocean, pressure gradients compress water according to equations of state that maintain density stratification and drive circulation patterns through abyssal depths where temperatures hover just above freezing. Hydrothermal vents release heated water enriched with sulfur compounds that support chemosynthetic ecosystems operating independently of solar energy, demonstrating how life exploits any available energy gradient for metabolism and growth. The deep sea continues its patient circulation through trenches and basins, mapped by sound waves but still largely unexplored by direct human observation. Stellar evolution proceeds according to nuclear fusion rates that will maintain solar energy output for several billion more years, providing the stable energy source that enabled biological evolution and will continue supporting planetary habitability through timeframes that encompass the entire future potential of technological civilization. The Sun's position within the galactic habitable zone remains stable as the solar system completes its orbital journey around the galactic center, maintaining the heavy element abundances and radiation environment that permit complex chemistry. Ice sheets in Greenland and Antarctica preserve atmospheric samples from hundreds of thousands of years in crystalline archives that record the planet's climate history with annual precision. Each layer contains trapped air bubbles that maintain ancient atmospheric compositions, creating libraries of environmental information that reveal how Earth's systems have responded to natural and human-caused changes. The ice continues accumulating new layers that will preserve records of the current epoch for future scientists to discover. Earth's rotation slows by microseconds each day as tidal forces gradually transfer angular momentum to the Moon's orbit, lengthening days according to celestial mechanical principles that have operated since the Moon's formation. The process will continue for billions of years until the planet becomes tidally locked to its satellite, creating a final configuration where one face permanently faces the Moon. Yet for now, the 24-hour day maintains the rhythm that has structured biological activity and human civilization throughout recorded history. Somewhere in the quantum foam of vacuum fluctuations, virtual particles appear and annihilate in accordance with uncertainty, principles that govern the fundamental structure of space and time. These microscopic events follow the same probabilistic laws that govern radioactive decay in Earth's interior, stellar nucleosynthesis in distant stars, and the genetic mutations that drive evolutionary change. Physics operates consistently across all scales, from subatomic to cosmic, maintaining the mathematical relationships that make the universe comprehensible to intelligence. The planet spins through space at its appointed distance from the Sun, following the same orbital mechanics that have maintained stable seasons and moderate climate throughout the development of consciousness. Earth continues its ancient project of supporting complexity and promoting the evolution of systems capable of understanding their own existence. In the quiet spaces between human thoughts, geological time unfolds according to physical laws that seem almost designed to create and sustain the very awareness that contemplates them. All systems operational. All parameters within acceptable ranges. The planetary engineering project continues, as it has for 4.5 billion years, with the patience of geological time and the precision of universal law